Reality is broken, not metaphorically, not as a figure of speech. Actually, genuinely, mathematically broken. There are contradictions woven into the fabric of existence so fundamental that the smartest minds in human history have spent centuries staring at them, and the contradictions have stared back, unchanged, unmoved, utterly indifferent to our confusion. A light beam that should reach you but never does. A night sky that should be blazing but sits in darkness. A cat that exists in two opposing states simultaneously, not in theory, but according to the actual mathematics that govern atomic reality. These are not riddles, they are not clever word games invented to make you feel stupid. They are paradoxes, places where the rules of the universe appear to eat themselves, where logic folds inward and our most carefully constructed models of reality start whispering that something essential is missing. And the most unsettling part, these paradoxes are not fringe ideas debated in obscure journals. They are cornerstone problems in physics, cosmology, and philosophy. Olbers asked why infinite starlight does not blind us. Fermi asked why 200 billion galaxies have produced absolute silence. Schrödinger built a thought experiment so disturbing it still haunts quantum mechanics 90 years later. Hawking discovered that black holes might be destroying information itself, violating the most sacred rule in physics. Zeno argued 2,500 years ago that motion is impossible, and we still teach his paradox because we still feel its sting. This is not a video about solutions. This is a video about the 10 places where reality stops making sense, where the universe hands us an equation that does not solve, a question that does not close, and what those cracks in logic reveal about the cosmos we are trying, and possibly failing, to understand. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. Look up. Go ahead. Wait until it's dark and step outside and tilt your head back and look at the sky. What do you see? Stars, sure, scattered points of light punched through a dark curtain, maybe a planet or two if you know where to look. Maybe the pale smear of the Milky Way if you're lucky enough to be far from city lights. But mostly, what you see is darkness. Black, empty space stretching between the stars, an ocean of nothing, punctuated by tiny islands of light. Now ask yourself a simple question. If the universe goes on forever, if space extends infinitely in every direction, and stars are scattered throughout that infinity more or less evenly, why is the night sky dark at all? Think about it. In an infinite universe filled with stars, every single line of sight from your eye should eventually intersect with the surface of a star. It doesn't matter if that star is 1,000,000 light-years away or 1,000,000,000,000. In infinity, every direction is eventually occupied. The sky shouldn't have gaps. It shouldn't have darkness. Every point, every pixel of the night sky above you should glow with the same blinding intensity as the surface of the sun. The entire dome of the heavens should be a seamless wall of starlight, so bright you couldn't look at it without going blind. The night sky should be an inferno. Instead, it's quiet, dark, gentle enough that you can stare at it for hours without discomfort. And that contradiction, that gap between what infinity predicts and what your eyes actually see, is one of the oldest and strangest problems in all of astronomy. It has a name, Olbers Paradox, and for more than 2 centuries it sat at the center of cosmology like a thorn nobody could pull out. The paradox is named after Heinrich Wilhelm Olbers, a German astronomer who described it formally in 1823. Olbers wasn't the first to notice the problem. A Swiss astronomer named Jean-Philippe de Chazot had written about it back in 1744, and there are hints that even earlier thinkers stumbled across the same question. But Olbers was the one who laid it out clearly, mathematically, in a way that forced the scientific community to take it seriously. He looked at the assumptions everyone was making about the universe, assumptions that seemed perfectly reasonable at the time, and showed that those assumptions led directly to an absurdity. Here were the assumptions. First, the universe is infinite. It has no edge, no boundary. Space goes on forever in every direction. Second, the universe is eternal. It has always existed and always will. There was no beginning, no moment of creation. Third, the universe is static. It isn't expanding or contracting. The distances between objects stay the same over time. Fourth, stars are distributed more or less uniformly throughout space. There are dense regions and sparse regions, but on average, if you zoom out far enough, the density evens out. And fifth, stars shine. They produce light, and that light travels outward in straight lines at a finite speed. None of those assumptions seemed crazy. In fact, most of them seemed obvious. The universe looked infinite. Nobody had found an edge. It looked eternal. There was no evidence of a beginning. It looked static. Galaxies weren't visibly moving, and stars were everywhere you pointed a telescope. So the logic held together. Except for one problem. The sky was dark. Olbers ran the math. Imagine you're standing in the center of a sphere. The sphere is filled with stars, all roughly the same brightness. Now imagine the sphere getting bigger. As the radius doubles, the surface area of the sphere increases by a factor of 4. That means 4 times as many stars fit inside. But those stars are also twice as far away, and light from a source falls off with the square of the distance. A star twice as far away appears 4 times dimmer. The two effects cancel out exactly. Double the radius, quadruple the number of stars, but each one is 4 times dimmer. The total brightness stays the same. Now keep expanding the sphere. Triple the radius, 10 times the radius, 1,000,000 times, infinity. In an infinite universe, you can keep stacking shells of stars outward forever, and each shell contributes the same total brightness as the one before it. Add up an infinite number of shells, each contributing a finite amount of light, and the total is infinite. The night sky should be infinitely bright. Or at least, since stars have finite surface brightness, every line of sight should eventually hit a star, making the sky as bright as the average stellar surface. For a star like the Sun, that's about 5,700 degrees Celsius, bright enough to vaporize you instantly. Bright enough that the Earth would never have cooled, bright enough that nothing remotely like life could exist. The universe clearly wasn't behaving that way, so something in the assumptions had to be wrong. But which one? The first instinct was to blame absorption. Maybe astronomers thought there's dust out there between the stars. Cosmic dust, clouds of gas and microscopic particles floating in the void. Light from distant stars hits the dust and gets absorbed before it reaches Earth. Problem solved. The distant stars are shining, but we can't see them because their light never makes it through. That explanation held up for a while. Then someone pointed out the flaw. Dust doesn't destroy light. It absorbs it, heats up, and then re-radiates the energy. If you put a dust cloud in front of a star, the dust will eventually reach thermal equilibrium with the radiation hitting it. It will glow. And if the universe is infinite and eternal, there's been infinite time for every dust cloud to heat up to the same temperature as the starlight passing through it. The dust would glow just as brightly as the stars it was blocking. Absorption doesn't solve the paradox, it just shifts the problem. The second attempt was to suggest that maybe stars aren't distributed uniformly. Maybe they're clumped together in groups, leaving vast stretches of empty space between them. If most of the universe is empty, most lines of sight would end in darkness. That sounds promising until you remember that we're talking about an infinite universe. Even if stars are clumped into galaxies, and galaxies are clumped into clusters, and clusters are separated by enormous voids, infinity gives you infinite clusters. Every line of sight, no matter how empty the space between clusters, will eventually intersect a cluster, and then a galaxy, and then a star. Clumping delays the problem. It doesn't erase it. The third idea was that maybe stars have short lifetimes. Maybe they only shine for a few million years before going dark, and the light from the most distant ones simply hasn't reached us yet. That gets closer to the truth, but it still doesn't work in an eternal universe. If the universe has existed forever, even short-lived stars would have had infinite time to light up, die, and be replaced. There would always be enough active stars at any given moment to fill the sky. Finite lifetimes help, but only if the universe itself hasn't been around forever. For more than a century, the paradox sat there. Olbers had no good answer, neither did anyone else. The assumptions seemed unshakable, and the contradiction refused to go away. Astronomers filed it under cosmic mysteries and moved on to problems they could actually solve. Then, in the early 20th century, everything changed. Two discoveries, both so profound that they rewrote cosmology from the ground up, finally cracked Olbers Paradox wide open. The first discovery was that the universe has an age. It isn't eternal, it had a beginning. The evidence came from multiple directions. Edwin Hubble's observations in the 1920s showed that distant galaxies were moving away from us, and the farther away they were, the faster they were receding. That meant the universe was expanding. Run the expansion backward, and everything converges to a single point, a moment of origin, the Big Bang. The universe, it turned out, was roughly 13.8 billion years old, not infinite in time. Finite, young, still a baby in cosmic terms. That alone solves most of Olbers' paradox. If the universe is only 13.8 billion years old, then light from stars more than 13.8 billion light-years away hasn't had time to reach us yet. There's a horizon, a boundary not in space but in time. Beyond that horizon, the universe exists, but its light is still in transit. It hasn't arrived. The night sky is dark because we're looking at a universe that hasn't finished filling in yet. The distant stars are shining, but their light is still on the way, crossing a gap that 13.8 billion years of travel time hasn't been enough to close. That's the primary resolution. The universe has a beginning. The sky is dark because the universe is young. Simple, elegant, and backed by mountains of observational data. But there's a second piece to the puzzle, and it's just as important. The universe isn't just expanding, it's accelerating. The space between galaxies is stretching, and as it stretches, it pulls the light traveling through it along for the ride. Light from a distant galaxy that started out in the visible spectrum, the blue and yellow and red that your eyes can see, gets stretched into longer and longer wavelengths as it crosses billions of light-years of expanding space. By the time it reaches Earth, that light has been redshifted. It's no longer visible, it's infrared, it's microwave, it's radio. Your eyes can't see it. It's still there, still carrying energy, but it's been stretched so far that it passes right through your retina without triggering a response. This is why the cosmic microwave background exists. In 1965, Two scientists named Arno Penzias and Robert Wilson were testing a radio antenna in New Jersey when they picked up a faint hiss of noise coming from every direction in the sky. They thought it was interference. They checked their equipment. They cleaned out pigeons nesting in the antenna. The noise didn't go away. What they were hearing was the stretched, cooled remnant of the Big Bang itself. Light that was once scorching hot, visible, ultraviolet, had been traveling for 13.8 billion years, and expansion had stretched it into microwaves. To your eyes, the cosmic microwave background is invisible. To a radio telescope, it's the brightest thing in the universe. Redshift doesn't just apply to the Big Bang, it applies to every distant galaxy. The farther away a galaxy is, the faster it's receding, and the more its light gets stretched. At extreme distances, galaxies that should be blazing bright in visible light arrive as faint infrared whispers. Their light is there, but it's been drained of energy, spread thin across wavelengths your biology wasn't built to detect. The night sky is dark, not just because the universe is young, but because the universe is running away from us, taking its light with it. Put the two explanations together, and you get the full answer. The sky is dark because the universe had a beginning, which means there's only so much light that's had time to reach us. And the sky is dark because the universe is expanding, which means the light that has reached us has been stretched and dimmed and redshifted into invisibility. Finite age and cosmic expansion, both are necessary, both are true. And both were completely unknown when Olbers first wrote down his paradox. There's a quantitative angle to this that's worth appreciating. For the night sky to be as bright as the surface of the sun in a static, eternal universe, the universe would need to extend at least 6.6 times 10 to the 15th light-years in every direction. That's a number so large, it makes the actual observable universe, with its radius of about 93 billion light-years, look like a rounding error. But even that wouldn't be enough if the universe were truly infinite. Infinity doesn't care about distance scaling. An infinite universe with uniform star density would still produce infinite brightness, no matter how far apart the stars were spaced. The only way out is to break one of the assumptions, and the assumption that broke was eternity. The universe is not eternal, it is not static, it is not infinite in time, and those facts, which we now take for granted, were unthinkable to most scientists in Olbers' era. The paradox wasn't just a curiosity, it was a clue, a crack in the foundation of classical cosmology. The dark sky was trying to tell us something. It took us 200 years to listen. Olbers himself never saw the resolution. He died in 1840, decades before Hubble's observations, more than a century before the discovery of the cosmic microwave background. He spent his life staring at a problem that looked unsolvable because the tools to solve it didn't exist yet. The answer required a completely different picture of the universe, one where time had a starting point and space itself could stretch. A picture that would have seemed like science fiction in 1823. The paradox also makes you realize how much we take darkness for granted. You walk outside at night and see a black sky dotted with stars, and it feels normal, unremarkable. But that darkness is one of the most important pieces of evidence we have about the nature of reality. It tells us the universe is young. It tells us space is expanding. It tells us there was a Big Bang. All of that information is encoded in the simple fact that when you look up, you see black instead of blinding light. There's something almost eerie about it. The absence of light is the signature of a cosmos with a beginning. If the universe were eternal, you wouldn't be here. The earth wouldn't be here. The night sky would be a furnace, and nothing remotely like structure or chemistry or life could survive. The fact that you can stand outside on a clear night and look up without your retinas burning out of your skull is proof that the universe had a birthday. And here's the thing, Olbers Paradox is just the start. It's the first crack, the first hint that the universe doesn't behave the way common sense says it should. The first paradox in a long line of paradoxes that force us to question our assumptions about space, time, causality, and existence itself. If a simple observation like a dark sky can hide such a profound truth, what else are we missing? What other contradictions are sitting right in front of us, waiting for someone to ask the right question? Because the universe doesn't just hide its secrets in distant galaxies or exotic particles, it hides them in plain sight, in the ordinary, in the things we see every night and never think to question. The dark sky was one of those things, and it turned out to be the door to an entirely new understanding of where we are and when we are, and how long everything has been here. But the universe has more doors, more paradoxes, and some of them don't involve looking up at the sky. Some of them involve looking out at the galaxy and asking a much simpler, much stranger question. If the universe is so vast, so old, so full of stars and planets, then where is everybody? The dark sky was the first paradox, the absence of light where logic said there should be infinite brightness. And solving it required us to accept that the universe had a beginning, that it was younger than we thought, that the cosmic clock had only been running for 13.8 billion years instead of forever. That realization opened the door to modern cosmology. It also opened the door to a much stranger question, one that doesn't require a telescope or a spectrograph or a deep understanding of redshift and expansion, one that only requires you to look at the numbers and ask a question so simple it sounds almost naive. If the universe is that old, and if our galaxy alone contains hundreds of billions of stars, and if a decent fraction of those stars have planets, and if a decent fraction of those planets are habitable, then where is everyone? That question has a name, the Fermi Paradox. And it has been sitting in the middle of astronomy, biology, philosophy, and planetary science for more than 70 years, like a puzzle piece that doesn't fit anywhere but refuses to be ignored. The story begins in the summer of 1950 at Los Alamos National Laboratory in New Mexico. Enrico Fermi, one of the architects of the atomic age, a man who had built the first nuclear reactor under a squash court in Chicago and helped design the bomb that ended World War II, was walking to lunch with a group of colleagues, Emil Konopinski, Edward Teller, Herbert York, big names, sharp minds, the kind of people who spent their mornings calculating neutron cross-sections and their afternoons casually discussing the fate of civilizations. The conversation that day had started with a topic that sounds absurd in hindsight, but was genuinely buzzing through the news at the time. A recent spate of UFO sightings and a cartoon in the New Yorker that joked about aliens stealing trash cans. The group was talking about faster-than-light travel, the likelihood of interstellar visitors, the usual mix of science and speculation that happens when physicists get bored. Then the conversation drifted. They talked about other things. They sat down to eat. And then, out of nowhere, Fermi spoke up. He said, "But where is everybody?" The question landed like a bomb, not because it was complicated, because it wasn't. It was so simple that everyone at the table immediately understood what he meant. If intelligent life is common in the universe, if civilizations arise on planets around other stars the way they arose here, if any of those civilizations develop technology even slightly more advanced than ours, then where are they? Why haven't we seen them? Why haven't they visited? Why isn't the galaxy teeming with signals, probes, megastructures, evidence of their existence? The silence at that table has echoed through the scientific community ever since. Fermi didn't write a paper. He didn't publish a formal argument. He asked a question over lunch and moved on. But the question stuck, because once you hear it, you can't unhear it. The numbers seem to demand that we should not be alone. The evidence suggests we are, and the gap between those two facts is enormous. Let's start with the numbers, because they're what make the paradox so uncomfortable. Our galaxy, the Milky Way, contains somewhere between 100 billion and 400 billion stars. The exact count depends on how you define a star and how you account for dim red dwarfs that are hard to detect. Let's be conservative and call it 200 billion. 200 billion suns scattered across a disk of stars roughly 100,000 light-years in diameter. For a long time, we didn't know how many of those stars had planets. Planets are small. They don't produce their own light. Detecting them from across interstellar distances is extraordinarily difficult. But in the last 30 years, that changed. The Kepler Space Telescope, launched in 2009, stared at a single patch of sky for years and watched for the tiny dip in brightness that happens when a planet crosses in front of its star. It found thousands of them, thousands, and from that sample, astronomers extrapolated. The current estimate is that nearly every star in the galaxy has at least one planet. Some have more. The galaxy isn't just full of stars, it's full of worlds. Not all of those worlds are habitable. Most are too hot, or too cold, or too massive, or orbiting stars that are too unstable. But even if you apply strict filters, only planets in the so-called habitable zone where liquid water can exist on the surface, only planets orbiting stable stars, only planets with the right size and the right atmosphere. Even then, the numbers are staggering. Conservative estimates suggest there could be tens of billions of potentially habitable planets in the Milky Way alone. Tens of billions. That's not counting the rest of the universe. That's just our galaxy. Now ask the next question. On how many of those planets did life actually arise? We don't know. We have one data point, Earth. Life appeared here relatively quickly. The planet formed about 4.5 billion years ago. The earliest evidence of life dates to at least 3.7 billion years ago, possibly earlier. Liquid water, organic chemistry, stable conditions, and within a few 100 million years, something was alive, replicating, evolving. That suggests life might not be that hard to start, or it suggests we got lucky. Or it suggests the definition of life is slippery and we're pattern matching where we shouldn't. The data doesn't tell us which. But let's be generous. Let's say life arises on 1% of habitable planets. That's still hundreds of millions of living worlds in the galaxy. Now ask the harder question. On how many of those worlds does life become complex, multicellular, intelligent, technological? That's where the numbers get uncomfortable. Because we only have one example of intelligence, and the path that led to us was long, fragile, and full of bottlenecks. Life on Earth spent billions of years as single-celled organisms. The jump to multicellularity didn't happen until about 600 million years ago. The jump to tool use didn't happen until a few million years ago. The jump to radio transmission didn't happen until 1900. And we've come close to destroying ourselves more than once in the decades since. Still, even if intelligence is rare, even if the odds of a planet producing a technological civilization are 1 in a million, you still end up with hundreds of civilizations in the galaxy. And that's where the paradox bites down, because we don't see them, not one. Not a single verified signal, not a single probe, not a single piece of evidence that anyone else is out there. The galaxy is quiet. Or at least, it's quiet in the frequencies we've been listening to with the instruments we've built. And the question Fermi asked is why. The Drake equation is often invoked here. It's a formula developed by astronomer Frank Drake in 1961, designed to estimate the number of detectable civilizations in the galaxy. It looks like this, in plain language. Start with the rate at which stars form. Multiply by the fraction of those stars that have planets. Multiply by the average number of planets per star that could support life. Multiply by the fraction where life actually arises. Multiply by the fraction where life becomes intelligent. Multiply by the fraction that develops technology capable of communication. Multiply by the length of time such civilizations broadcast detectable signals. Plug in optimistic numbers and you get thousands of civilizations. Plug in pessimistic numbers and you get less than one. Plug in realistic numbers and you get a range so wide it's almost meaningless. The equation isn't predictive, it's a framework, a way to organize ignorance. But it does make one thing clear: the final term, the length of time a civilization remains detectable, matters enormously. A civilization that lasts 1,000,000 years will be far more likely to overlap with us in time than one that lasts 1,000. And a civilization that lasts only a century before destroying itself or going silent might as well not exist. That brings us to the first major explanation for the paradox: the great filter. The idea is simple and terrifying. Somewhere between the formation of a planet and the development of a galaxy-spanning civilization, there is a bottleneck. A step so difficult, so unlikely, that almost no one makes it through. Life hits a wall. And the filter is so effective that the galaxy is full of dead worlds, sterile worlds, worlds where something went wrong before intelligence ever had a chance to arise, or where intelligence arose and then wiped itself out. The question is where the filter sits. If it's behind us, if the hard step was the origin of life, or the jump to multicellularity, or the evolution of intelligence, then we're safe. We've already passed the test. We're the lucky ones. The galaxy is empty not because civilizations destroy themselves, but because they never form in the first place. We're alone because getting to where we are is almost impossibly hard, and we happen to win a cosmic lottery. If the filter is ahead of us, the picture is much darker. It means the hard step is still coming. It means most civilizations that reach our level of development don't make it much further. They destroy themselves through war, environmental collapse, resource depletion, runaway artificial intelligence, engineered pandemics, or something we haven't thought of yet. The galaxy is quiet because every civilization that gets loud eventually goes silent. And if that's true, then our future is already written. We're not special, we're not immune, we're just next in line. Carl Sagan and Iosif Shklovsky speculated in 1966 that technological civilizations likely destroy themselves within a century of developing interstellar communication. A century. We've had radio for about 120 years. We've had nuclear weapons for 80. We've had the internet for 30. If Sagan was right, we're living on borrowed time. The filter isn't some abstract evolutionary hurdle. It's us, our own capacity for self-destruction. And the silence of the galaxy is the echo of 1,000,000 worlds that didn't make it. There's a counter-argument. Maybe the filter is survivable, but only barely. Maybe some civilizations make it through and go on to live for billions of years. But the transition is so traumatic, so close to extinction, that only a tiny fraction survive. The galaxy could be full of ancient civilizations that figured out how to not kill themselves, but they figured it out the hard way, and they learnt to be quiet. Which brings us to the second category of explanations. They're out there, but we can't see them. The zoo hypothesis, proposed by astronomer John Ball in 1973, suggests that extraterrestrial civilizations know we're here. They're watching, but they've made a deliberate choice not to interfere. We're a protected species, a nature preserve, a cosmic exhibit under observation. Maybe there's a galactic ethical code. Maybe advanced civilizations have agreed that primitive species like us should be left alone to develop naturally. First contact only happens when a species reaches a certain threshold of maturity. We haven't reached it yet, so they wait. It sounds comforting until you think about the implications. If the zoo hypothesis is true, it means someone is watching right now, monitoring our television broadcasts, our internet traffic, our wars and art and scientific progress, and they've decided we're not ready. We're the equivalent of uncontacted tribes in the Amazon. Interesting to study, not ready for inclusion. The galaxy has a club, and we're not invited. The dark forest theory takes the idea in a much bleaker direction. It's named after a science fiction novel by Liu Cixin, but the concept predates the book. The logic goes like this. The universe is a dark forest. Every civilization is a hunter moving quietly through the trees. You don't know who else is out there. You don't know their intentions. You don't know if they're hostile or peaceful, stronger or weaker, desperate or secure. The only thing you know for certain is that if you reveal your location, you're taking a risk. Because if another civilization finds you and decides you're a threat, they can destroy you before you even know they're coming. The safest strategy is silence. Don't broadcast. Don't build megastructures that shine like beacons. Stay dark, stay hidden, survive. If that's the rule most civilizations follow, then the galaxy could be full of life, and we'd never know. Everyone is hiding. The silence isn't absence, it's fear. Then there's the rare Earth hypothesis. The argument here is that simple life might be common, but complex life, intelligent life, technological life is extraordinarily rare. Earth didn't just get lucky once, it got lucky a dozen times. We have a large moon that stabilizes our axial tilt. We have Jupiter acting as a cosmic vacuum cleaner, deflecting asteroids that would otherwise pummel us. We have plate tectonics that recycle carbon and maintain a stable climate. We have a magnetic field that shields us from radiation. We're in the right part of the galaxy, far from the chaotic core, in a quiet stellar neighborhood. Stack all those conditions together, and maybe planets like Earth aren't 1 in a million. Maybe they're 1 in a trillion. Maybe we're not just rare. Maybe we're unique. The problem with all these explanations is that they're unfalsifiable. You can't prove the zoo hypothesis wrong. You can't prove the dark forest theory wrong. You can't prove rare Earth wrong until we've surveyed every planet in the galaxy and found nothing. Each explanation makes sense in isolation. None of them can be tested. And that makes the Fermi Paradox less a scientific problem and more a philosophical one. A mirror we hold up to ourselves to see what we believe about the universe and our place in it. Fermi himself, according to people who were at that lunch, probably believed the answer was simpler. Interstellar travel is hard. Space is enormous. The distances between stars are measured in light years. Even if civilizations exist, even if some of them have technology far beyond ours, it doesn't mean they can cross the galaxy. They're stuck in their own solar systems, the same way we're stuck in ours. The galaxy could be full of islands of intelligence, each one isolated, each one alone, separated by gulfs of space so vast that contact is effectively impossible. We're not being avoided, we're not being watched. We just haven't been reached yet, and maybe we never will be. There's one more angle worth considering. Maybe we're listening wrong. We've been scanning the skies for radio signals since the 1960s. SETI, The search for extraterrestrial intelligence has spent decades pointing radio telescopes at nearby stars, listening for patterns that can't be explained by natural processes. So far, nothing. A few false alarms. A lot of noise. No confirmed signals. But radio is a narrow slice of the electromagnetic spectrum. It's also a brief phase of technological development. We've only been broadcasting radio for about a century. In another century, we might move to something more efficient. Laser communication, quantum entanglement, something we haven't invented yet. If other civilizations followed the same path, their radio phase might have lasted a few hundred years out of a million-year lifespan. We could be listening at the wrong time, in the wrong way, with the wrong tools. Or maybe intelligence just isn't the inevitable endpoint of evolution. Maybe it's a fluke, a one-time accident that happened here because a specific sequence of environmental pressures and random mutations lined up in a way that will never be repeated. Dinosaurs ruled the Earth for 160 million years and never developed technology. Octopuses are astonishingly intelligent and have been around for 300 million years, and they've never built cities. Intelligence isn't a goal. Evolution doesn't have goals. It's a random walk through possibility space, and most paths don't lead to radio telescopes. The Fermi Paradox doesn't have an answer. Not yet. Maybe not ever. What it has is implications. If the great filter is behind us, we're miraculous. If it's ahead of us, we're doomed. If the galaxy is full of life and we just can't see it, we're blind. If we're alone, we're unspeakably precious. Every possible resolution changes the way we should think about ourselves. Fermi asked his question in 1950. We're still asking it. Still building bigger telescopes, still listening to more frequencies, still searching for biosignatures in the atmospheres of distant planets. And the silence continues. The galaxy remains quiet, or at least it seems that way from where we're standing. But absence of evidence is not evidence of absence. The paradox is unresolved, and that unresolved status is itself a kind of answer. It tells us we don't know as much as we think we do. It tells us the universe is under no obligation to behave the way our equations predict. And it tells us that the question, where is everybody, might be less important than the question it leads to. What happens next? What happens when a species like ours, fragile and violent and brilliant and self-destructive, reaches the point where it can see across the galaxy and realizes it's alone? Or worse, realizes it might not be, that the silence might be a warning? Those are questions about the future. But the next paradox we're going to look at isn't about what's out there. It's about what's back here, about time itself, about whether the past is fixed or flexible, about what happens when you try to rewrite your own history, and whether the universe will let you. The Fermi Paradox left us staring at the silence of the galaxy, wondering whether we're alone or just deaf. Either answer is unsettling, but at least when we're asking where the aliens are, we're looking outward. The next paradox pulls us somewhere closer, not across space, but across time. And it doesn't ask whether other intelligences exist. It asks whether you can erase your own existence, whether the past is something you can touch, change, unmake, whether time is a river you can dam or a concrete slab that won't budge no matter how hard you push. This is the grandfather paradox, and if you've heard of time travel, you've probably heard of this. It's the oldest, simplest, most direct argument against the possibility of traveling backward through time. The setup is absurdly straightforward. You build a time machine. You travel back to a point before your parents were born. You find your grandfather as a young man, before he's met your grandmother, before he's had children, and you kill him. You prevent his lineage. You erase the branch of the family tree that leads to you. And the moment you do that, you create a problem that logic cannot solve. If your grandfather dies before your parents are born, then your parents are never born. If your parents are never born, then you are never born. If you are never born, then you never build a time machine. If you never build a time machine, you never travel back in time. If you never travel back, you never kill your grandfather. If you never kill your grandfather, he lives. Your parents are born, you are born. You build a time machine, you travel back, you kill him. The loop closes, the paradox eats its own tail. This isn't a trick. It's not a puzzle with a clever solution hiding in the wording. It's a direct contradiction. A situation where both outcomes, the grandfather lives and the grandfather dies, lead to their own negation. You can't have it both ways, and you can't have it either way. The event destroys its own cause, and the absence of the event allows the cause to exist. Causality, the bedrock rule that effects follow causes, snaps in half. The paradox was first described in fiction. Science fiction writers got there before physicists did, which is often the case when you're dealing with ideas too strange for equations to catch up to immediately. Nathaniel Schachner wrote about it in a short story. René Barjavel explored it in his 1943 novel, Future Times 3, originally titled Le Voyageur Imprudent, The Careless Traveler. Barjavel's version was blunt. A man travels back, kills his ancestor before any children are born, and the book ends with the main character flickering out of existence mid-sentence. No resolution, no escape. Just the cold logic of the paradox closing around him like a trap. For decades, this was treated as the ultimate refutation of backward time travel. If allowing people to travel into the past leads directly to logical impossibilities, then the past must be off-limits. Time only moves forward. The universe doesn't permit paradoxes, so it doesn't permit time machines. Case closed. Except physics doesn't work that way. You don't get to dismiss an idea just because it's uncomfortable. You have to show why the universe forbids it, mechanically, with rules and equations. And when physicists started taking time travel seriously in the latter half of the 20th century, they realized the universe might have answers. Strange answers, uncomfortable answers, but answers. The first serious response came from Igor Dmitrievich Novikov, a Russian astrophysicist who spent much of his career working on black holes, cosmology, and the nature of space-time. In the 1980s and 90s, Novikov and his colleagues developed what's now called the Novikov self-consistency principle. The idea is deceptively simple. If time travel to the past is possible, then the universe only allows events that are self-consistent. You can travel back in time, yes, but you cannot do anything that creates a paradox, not because you choose not to, because you physically can't. The universe won't let you. Picture it this way. You step out of your time machine in 1925 with a gun in your hand and murder on your mind. You find your grandfather. You aim. You pull the trigger. The gun misfires. You try again. It jams. You grab a rock. You trip. You try to push him in front of a car. He steps back at the last second. Every single attempt fails. Not because of luck, not because of coincidence, because the timeline you're standing in already includes your existence in the future. You were born, that's a fact. That's already happened from the universe's perspective. And because you were born, your grandfather lived long enough to have children. That's also a fact. The past is fixed, not because it's written in stone, but because it's already written. It's already part of the four-dimensional structure of space-time. You can go back and participate in it, but you can't rewrite it. You were always part of it. You always failed to kill him. This resolves the paradox by denying its premise. There is no version of events where the grandfather dies before having children, because if there were, you wouldn't exist to go back and kill him. The timeline is a closed loop, consistent, self-fulfilling. You can interact with the past, but only in ways that preserve the future you came from. The universe enforces this not through some kind of cosmic referee, but through the basic structure of cause and effect. If an event leads to a contradiction, that event doesn't happen. The probability of it happening drops to exactly zero. The same way the probability of a ball rolling uphill without any external force drops to zero. It's not forbidden by law, it's forbidden by consistency. The Novikov principle has a certain elegance to it. It doesn't ban time travel, it just puts guardrails on it. You can visit the past, you can witness events, you can even participate, but you can't change anything that would prevent your own departure. You're a part of history, not an editor. Your actions were always part of what happened. This is sometimes called the billiard ball model, based on a thought experiment involving a wormhole and a billiard ball that travels back in time and collides with its earlier self. The collision has to happen in such a way that the ball still enters the wormhole. There are multiple possible trajectories that satisfy this requirement, but none that create a paradox. The universe picks one. Consistency wins. Critics of the Novikov principle point out that it feels uncomfortably deterministic. It implies that free will, at least in the context of time travel, is an illusion. You think you're choosing to pull the trigger, but the universe has already decided the gun will jam. You think you're choosing to push your grandfather, but the universe has already decided he'll step aside. Your choices are constrained by the requirement that the timeline remain consistent. You're not free. You're a chess piece moving along a predetermined path. And if that's true in the past, is it true in the present? Is everything predetermined? The paradox starts to bleed into philosophy, into questions about determinism and agency that go way beyond time machines. The second major solution takes a completely different approach. Instead of preserving a single timeline, it creates new ones. This is the many worlds interpretation, the multiverse model, and it comes originally from quantum mechanics, not from time travel fiction. Hugh Everett proposed it in 1957 as a way to understand what happens during quantum measurements. Every time a quantum event has multiple possible outcomes, the universe splits. Both outcomes happen. Each one occurs in a separate branch of reality. You measure a particle's spin. In one universe, it's up. In another, it's down. Both branches are real. Both continue forward. You just happen to be conscious in one of them. Apply that idea to time travel and the grandfather paradox dissolves. You travel back. You kill your grandfather, but the moment you do, you create a new timeline, a branch, an alternate history. In that branch, your grandfather dies young. Your parents are never born. You are never born. Fine, that's that timeline's problem. The original timeline, the one you left, still exists. In that timeline, your grandfather lived, your parents were born, you were born, you built a time machine, and you left. Nothing about killing your grandfather in the new branch erases the old branch. You're not erasing yourself, you're creating a universe where you never existed, but you still exist in the universe you came from. This model is conceptually cleaner in some ways. No mysterious forces preventing you from pulling the trigger. No cosmic enforcement of consistency. You have free will. You can do whatever you want in the past. The cost is that the past you're changing isn't your past anymore. It's a copy, an alternate version. You're not rewriting history. You're authoring a new one. The old one is still back there, untouched, running parallel. You've just stepped off the main track onto a siding. The many worlds model has its own problems. For one, it implies an infinite or near infinite proliferation of timelines. Every time traveler creates a new branch, every decision they make creates more branches. Every quantum event they interact with splits the timeline further. The number of universes explodes. Occam's razor, the principle that the simplest explanation is usually the right one, starts groaning under the weight. You're multiplying entities like rabbits to avoid a paradox. That doesn't mean it's wrong, but it does mean it's expensive in terms of ontological commitment. You're saying that every possible version of history exists somewhere, all running simultaneously, just to allow time travelers to avoid contradictions. There's also the question of whether you can ever get back. If killing your grandfather creates a new timeline, and you want to return to your own time, which timeline do you return to? The original, where you still exist, or the new one, where you were never born? Some models suggest you're stuck in the branch you created. You've left your home universe permanently. Other models suggest the time machine is somehow anchored to your original timeline, and traveling forward brings you back to it. But that raises even stranger questions about how the machine knows which branch is the right one. What defines your home timeline once you've split away from it? The multiverse solution trades one kind of strangeness for another. The Novikov principle makes the universe deterministic and strips away your ability to change the past. The many worlds model preserves your free will, but fills the cosmos with infinite parallel realities that you can never visit or verify. Both answers work logically. Neither one feels comfortable. There's a third option, quieter, less discussed. Maybe time travel to the past is just impossible. Not because of paradoxes, but because the structure of space-time doesn't allow it. General relativity, Einstein's theory of gravity, permits solutions that look like time travel, closed time-like curves, paths through space-time that loop back on themselves. Wormholes, tunnels connecting distant points in space and time. Rotating black holes, which under certain conditions might allow objects to move backward in time relative to the outside universe. The math allows these things, but the math also allows a lot of things that don't happen in practice. Stephen Hawking proposed what he called the chronology protection conjecture. The idea is that the laws of physics conspire to prevent the formation of closed time-like curves. Every time you try to build a time machine, something goes wrong. The energy requirements become infinite. The wormhole collapses. Quantum effects destabilize the structure. Hawking suggested that nature abhors a time machine, and the universe has built-in mechanisms to prevent them from ever being constructed. It's not a proof, it's a conjecture, but it has the virtue of simplicity. If time machines don't exist, then paradoxes don't exist. The grandfather paradox becomes a non-problem, a fun thought experiment with no practical implications. Still, the paradox lingers, because even if backward time travel is impossible, the logic of the paradox touches something deeper. It exposes a tension between our intuitive understanding of time and the way time actually behaves in physics. We experience time as a flow. Past, present, future. Causes lead to effects. Events unfold in sequence. That's how it feels. But relativity treats time as a dimension, not fundamentally different from space. The past doesn't vanish. It's still there, a region of space-time that you've moved away from. The future isn't unformed. It's another region you haven't reached yet. If time is just another direction, then moving backward should be no stranger than moving left. But our intuition rebels. Moving backward feels impossible, not because of the physics, but because of the causality. Effects don't precede causes. That rule feels unbreakable. The grandfather paradox asks, what happens if you break it? One way to think about the paradox is that it's testing the limits of causality itself. Causality is the principle that every event has a cause that comes before it in time. It's one of the foundational assumptions of all science. You can't have smoke without fire. You can't have a broken window without something that broke it. You can't have a corpse without something that killed it. Causality is the chain that links events together into a coherent timeline. The grandfather paradox asks whether that chain can loop, whether an event can be its own ancestor, its own cause, and the answer, at least in classical logic, is no. You can't have a causal loop that contradicts itself. Either the loop is consistent, which is what Novikov says, or the loop splits into branches, which is what many worlds says. But a self-negating loop, a loop where the effect prevents the cause, cannot exist. The universe doesn't allow it. Interestingly, quantum mechanics has its own version of this issue. Experiments with delayed choice setups and quantum erasers show that measurements in the present can appear to affect the behavior of particles in the past. Not in a way that violates causality, but in a way that makes the timeline look far less straightforward than common sense suggests. The past isn't always as fixed as it seems, or rather, what we call the past is observer-dependent, influenced by what measurements we choose to make now. Time at the quantum level is slippery. That doesn't mean you can kill your grandfather, but it does mean that the relationship between past, present, and future is more complicated than the paradox assumes. The grandfather paradox also has a quieter sibling. Instead of killing your grandfather, imagine you travel back and prevent your parents from meeting. Same outcome, less violent. Or imagine you travel back and accidentally cause the event that leads to your own conception. You introduce your grandparents at a party. They fall in love. They have children. One of those children is your parent. You caused your own existence. That's not a paradox in the same way. It's a closed causal loop, but a consistent one. You exist because you traveled back, and you traveled back because you exist. The loop has no beginning, it just is. That's called a Bootstrap Paradox, and it's the next step down this rabbit hole. But we'll get to that. For now, the grandfather paradox sits in the middle of physics and philosophy like a landmine. It hasn't been resolved, it's been worked around. The Novikov principle works around it by forbidding inconsistencies. The many worlds model works around it by creating new timelines. The chronology protection conjecture works around it by banning time travel altogether. But none of those solutions feel final. They all have costs. They all require us to accept something strange about the universe. Determinism, infinite branching realities, fundamental prohibitions on certain kinds of motion through space-time. Pick your poison. What the paradox really reveals is that time is not what we thought it was. It's not a simple one-way corridor. It's not a river that only flows downstream. It's something weirder, something more structural, something that doesn't easily accommodate our intuitive notions of past and future and change. We think of the past as gone, the future as open. But if relativity is right, both exist simultaneously, laid out in 4 dimensions like a map. You can't change the map. You're part of the map. Every event, every moment, every choice you've ever made or will make is already there, already real, already embedded in the structure. You don't travel through time, you exist across it. And if that's true, then the grandfather paradox isn't asking whether you can change the past. It's asking whether change even means anything when past, present, and future are all equally real, all equally fixed, all equally now. The paradox doesn't give us an answer. It gives us a question that cuts deeper the longer you stare at it. Can the past be altered? If it can, what happens to causality? If it can't, What happens to free will? And if time travel is possible, are you the author of history or just a character reading lines that were written long before you arrived? Those questions don't stop at grandfathers and time machines, because the next paradox takes the loop one step further. Instead of traveling back to destroy something, imagine traveling back to create something, an object, an idea, a piece of information that has no origin, that was never invented, never discovered, never brought into existence by any process. It just loops endlessly. And the question it asks is even stranger. Can something exist without a cause? The grandfather paradox asked whether you could erase your own existence, whether the past was something you could break. The answer, depending on who you ask, is either no, the universe won't let you, or yes, but only by creating a new timeline where you never existed in the first place. Either way, the paradox hinges on contradiction. You can't exist and not exist at the same time. The logic snaps. The loop collapses. Causality refuses to cooperate. But there's another kind of time travel paradox, one that doesn't involve murder or self-erasure or dramatic confrontations with your ancestors, one that's quieter, stranger, and in some ways more disturbing because it doesn't break logic at all. It obeys every rule. It creates no contradictions. It just removes something we thought was fundamental to reality. The concept of origin. The idea that everything must come from something, that every effect has a cause, and that if you trace the chain back far enough, you'll find a beginning. This is the Bootstrap Paradox. And unlike the grandfather paradox, which screams at you, this one whispers. It says, what if something could exist without ever being created? What if an object or a piece of information could loop through time endlessly, with no starting point, no inventor, no moment of birth? What if the chain of causality formed a perfect circle, with every link connected to the next, and no link connected to anything outside the loop? The paradox doesn't contradict itself. It just sits there, internally consistent, logically sound, and completely impossible to reconcile with the way we think the universe works. The name comes from the old idiom about pulling yourself up by your bootstraps. The phrase describes doing something impossible, lifting yourself off the ground by tugging on the straps of your own boots. It's absurd. You can't generate upward force by pulling on yourself. There's no external anchor, no leverage, and yet the Bootstrap Paradox describes exactly that kind of self-contained loop, something that exists because it exists, something that creates itself by already existing. Here's the simplest version. You're a time traveler. You step out of your machine in the year 2025 carrying a book, not just any book. A book containing scientific knowledge that hasn't been discovered yet. Equations for faster-than-light travel, maybe. Or a cure for cancer, or a detailed blueprint for a quantum computer. You hand the book to a young scientist. She reads it. She's brilliant. She understands it immediately. She publishes the findings. She becomes famous. Decades pass. The knowledge in the book becomes the foundation of an entire field of study. Technologies are built, lives are saved, and then, years later, that same scientist, now old, hands the book to you. She says, "Take this, you'll know what to do with it." You step into your time machine and travel back to 2025, where you hand the book to her younger self. The loop closes. Now ask the question. Who wrote the book? Not the scientist. She got it from you. Not you. You got it from her. The information exists. It's real. It works. People used it, but it was never created. It has no author, no inventor, no point of origin. It just loops endlessly. a closed circle of causality where every event is caused by the event after it, and the chain has no beginning. That's the Bootstrap Paradox. And the deeply uncomfortable thing about it is that it doesn't break any logical rules. There's no contradiction. The timeline is self-consistent. The book exists in year 2025 because you brought it from the future. You brought it from the future because the scientist gave it to you. The scientist gave it to you because she received it from you in the past. Every step follows from the one before it. Locally, at every point in the loop, causality works fine. Globally, when you zoom out and look at the whole structure, causality has no anchor. The loop is floating, self-sustaining, impossible. The paradox gets its other name, the ontological paradox, from the branch of philosophy called ontology, the study of existence, what it means for something to be. And this paradox cuts right to the heart of that question. Can something exist without a cause? Can information, an idea, a piece of knowledge, just be, without ever having been thought up by anyone? Our intuition says no. Everything comes from somewhere. But the Bootstrap Paradox says maybe not. Maybe, in a universe where time travel is possible, existence and origin are not the same thing. Maybe you can have a complete causal story without an origin story. One of the most famous fictional examples comes from a Doctor Who episode. Although the idea predates the show by decades, the Doctor, a time traveler, meets Beethoven. Except when he arrives in Beethoven's time, he discovers Beethoven doesn't exist, never existed. There is no composer by that name, but the Doctor has Beethoven's music. He's carrying the sheet music with him, so he publishes it under Beethoven's name. The music becomes famous. The world believes Beethoven was real, and the Doctor, in the future, learns about Beethoven from history books and carries the music back with him to complete the loop. The question the episode asks out loud is simple. Who wrote Beethoven's symphonies? Nobody. The music exists, but it was never composed. It copied itself through time. Replace music with anything else, and the paradox holds. A scientific theory, a technological blueprint, a piece of art, a mathematical proof. Anything that can be recorded, transmitted, and understood can theoretically be caught in a bootstrap loop. And once it's in the loop, it has no origin. It's not that we don't know where it came from, it's that there is no where it came from. The loop is the only explanation, and the loop explains everything except the one thing we think matters most, the beginning. This is fundamentally different from the grandfather paradox. The grandfather paradox creates a logical contradiction. You exist and you don't exist. Both statements are true and both are false. The timeline eats itself. The Bootstrap Paradox creates no contradiction. The timeline is perfectly consistent. The problem isn't logical, it's ontological. It's not that the events can't happen, it's that they seem to violate the principle that everything must have an origin, that for every created thing there must be a creator. That information doesn't spontaneously exist. It has to be thought up, discovered, invented, derived from prior knowledge. The bootstrap loop says no. Information can just loop, and once it's looping, it exists without ever having been created. Physicists who study time travel, the ones who take closed time-like curves seriously, have a name for this. They call it an information loop. And some of them argue that information loops are not just possible, but inevitable if backward time travel exists. If you can send information into the past, and that information can influence the future, and the future can send information back to the past, then under certain conditions, the information will settle into a stable loop. The loop doesn't need an external source, it's self-reinforcing. Any information that doesn't fit the loop gets edited out by the structure of causality itself. Only the error-free, self-consistent data survives. The loop selects for its own stability. That's a strange way to think about it, but it matches what some theoretical models predict. If you try to send a message back in time, and that message contradicts the past, the contradiction prevents the message from being sent. The timeline doesn't break, it adjusts. Only messages that preserve consistency can complete the loop. And once a loop is established, it's locked in. The information just circulates. No beginning, no end, just a closed curve in space-time where the future depends on the past and the past depends on the future, and neither one came first. Here's a concrete thought experiment that makes the problem sharper. Imagine you find a box in your attic. Inside the box is a blueprint for a time machine. You don't know where it came from. Your grandfather left it to you in his will, but he never told you where he got it. You're an engineer. The blueprint makes sense. You build the machine. It works. You use it to travel back in time. You meet your grandfather as a young man. You give him the blueprint. He stores it. Years later, he leaves it to you. The loop closes. Now ask, who designed the time machine? You didn't. You just followed the blueprint. Your grandfather didn't. He just passed it along. The blueprint exists. The machine works. You built it. But the design has no designer. The knowledge came from nowhere. It appeared out of the structure of the loop itself. You can trace every causal link. You got it from your grandfather. He got it from you. You gave it to him because you traveled back. You traveled back because you built the machine. You built the machine because you had the blueprint. Every step is explained, but the origin is missing. The loop explains how the blueprint moves through time. It doesn't explain how it came into existence. Some philosophers argue that this is proof time travel to the past is impossible. Not because of contradictions, but because of this. Because the Bootstrap Paradox, while logically consistent, is ontologically absurd. It asks us to accept that things can exist without being created, that knowledge can appear from nothing. That the question, where did this come from, can have the answer nowhere as a legitimate response, and that feels wrong. Not mathematically wrong, intuitively wrong. It offends our sense of how reality is supposed to work. Others argue the opposite. They say the Bootstrap Paradox reveals a bias in our thinking. We assume everything needs an origin because in our everyday experience, everything does. You trace the history of any object and you find a point where it was made. You trace the history of any idea and you find the person who thought of it first. But that's because we don't live in a universe with closed time-like curves. We live in a universe where time only moves forward, where causality is linear, where the past is always earlier than the future. In that kind of universe, yes, everything has an origin. But in a universe where time can loop, where the future can influence the past, the rules change. Causality doesn't have to be linear, it can be circular. And in a circular causal structure, the concept of an origin stops making sense. The loop is the origin. The loop is the explanation. There is no deeper answer. That argument has a certain elegance to it, but it also has a cost. If you accept that information can exist without an origin, then you're accepting that the past is not fully independent of the future, that what happens tomorrow can determine what happened yesterday, that history is not a sequence of events unfolding forward, but a four-dimensional structure where every point is connected to every other point, and the direction of time is just a label, not a rule. That's a strange universe to live in, a universe where the past is negotiable, where cause and effect are tangled together so tightly you can't separate them, where asking who came first is like asking which came first, the North Pole or the South Pole. The question assumes a linear structure that doesn't exist. The Bootstrap Paradox also raises uncomfortable questions about creativity and originality. If a piece of music, or a novel, or a scientific theory can exist in a loop, then what does it mean to create something? If Shakespeare's plays could, in theory, be brought back from the future and given to Shakespeare, who never actually writes them, just copies them and claims credit, then did he create them? He didn't think of the words, he didn't invent the characters, he just transcribed. But the plays exist. They're performed, they're studied, they're real, and there's no version of history where someone sat down and wrote them for the first time. They've always existed in the loop. The act of creation never happened. The plays are authorless. That's deeply strange if you think about it, because we define art and science and invention by the act of creation, by someone having an idea that didn't exist before, by originality, by the moment where something new enters the world. The Bootstrap Paradox suggests that in a universe with time travel, that moment might not exist. The new thing might not be new. It might just be old in a way that loops back on itself. The timeline might contain ideas that no one ever had, music that no one ever composed, theories that no one ever derived. They just are. Eternal, self-contained, uncreated. Philosophers call this the problem of uncaused causes, or sometimes self-caused causes. Every event in the loop is caused by another event in the loop. Locally, causality is preserved, but the loop itself, as a whole, has no external cause. It exists because it exists. It's a causal structure that bootstraps itself into being. And if you accept that such a structure is possible, then you're accepting that the universe can contain things that are fully explained without reference to anything outside themselves. That's not how we usually think about explanation. Usually, to explain something means to point to something else, to trace the chain back. But in a bootstrap loop, the chain is closed. There's nothing outside it to point to. The loop is its own explanation, and that explanation is complete, even though it contains no origin. There's a connection here to physics. In general relativity, Einstein's theory of spacetime, certain solutions allow for closed time-like curves, paths through spacetime that loop back on themselves. If you follow one of these paths, you can travel into your own past. You can meet your younger self. You can interact with events that, from your perspective, already happened. And if closed time-like curves are real, if they exist as physical structures in the universe, then bootstrap paradoxes are not just thought experiments, they're real possibilities. Objects or information traveling along a closed time-like curve would, by definition, form a causal loop. They would exist without an origin. The physics allows it. The math works. The question is whether the universe actually contains these structures, or whether some other law of physics steps in to forbid them. Stephen Hawking thought they were forbidden. His chronology protection conjecture, which we touched on in the last chapter, suggests that nature prevents closed time-like curves from forming. Not because they're logically impossible, but because they lead to situations that are ontologically bizarre. Situations where information has no source, where causality loops back on itself, where the past depends on the future in ways that feel fundamentally wrong. Hawking argued that the universe has mechanisms, probably involving quantum effects, that destabilize any structure that might allow backward time travel. The Bootstrap Paradox doesn't happen because time machines don't exist. Problem solved. But not everyone agrees. Some physicists argue that closed time-like curves might exist in very specific, very exotic conditions, near rotating black holes, inside certain configurations of wormholes, in regions of spacetime so warped and strange that the normal rules don't apply. If those structures exist, and if they can be traversed, then bootstrap loops are possible. And if they're possible, then the universe contains information without origin, ideas without authors, objects without creation. That's not a contradiction. It's just a feature of a universe where time can bend back on itself. Strange, yes. Uncomfortable, absolutely, but not impossible. There's also a version of the Bootstrap Paradox that's less about objects or information and more about events. Imagine you travel back in time and cause the event that led to your decision to time travel. Maybe you meet a younger version of yourself and inspire them to become a scientist. That younger version grows up, builds a time machine, travels back, and inspires their younger self. The loop closes. You became a scientist because your future self inspired you. Your future self traveled back because they were a scientist. The motivation is self-caused. The loop sustains itself. And there's no version of history where you decided to become a scientist for any external reason. The decision only exists within the loop. This version of the paradox is sometimes called a predestination loop. It suggests that if time travel is possible, certain events might be inevitable. Not because they're determined by the laws of physics, but because they're required by the structure of the timeline. If the loop exists, then every event in the loop must happen. You don't have a choice. You have to inspire your younger self because you were inspired by your older self. The timeline is fixed, not because someone fixed it, but because it's a closed structure, a loop with no exits. And if you're part of the loop, you're stuck in it. Free will doesn't enter the picture. You're playing a role in a script that's already written, a script that writes itself, a script that has no author. That's a disturbing picture. It suggests that in a universe with time travel, certain actions are not just likely but necessary, that the timeline can contain events that must happen in order for the timeline itself to be consistent, that the universe enforces its own consistency by constraining what you can do, not through physical force, but through logical necessity. The past happened the way it did because the future required it. The future happens the way it does because the past required it, and the loop just sits there, closed and stable and completely deterministic. Contrast that with the Grandfather Paradox, which is all about contradiction and impossibility. The Bootstrap Paradox doesn't contradict itself. It just removes the concept of a beginning. It says, here's a causal loop. Every event in it is caused by another event in it. The loop is self-consistent. The loop is stable. The loop exists. And there's no point in the loop where something was created for the first time. Creation doesn't happen. The loop just is, always has been, always will be. As long as the loop exists, the contents of the loop exist. And asking where the contents came from is like asking where the loop came from. The answer is, the loop came from the loop. It's circular, it's self-referential, it's complete, and it has no origin. If that makes you uncomfortable, you're not alone. Most physicists who think about this seriously end up in one of two camps. Either they accept that bootstrap loops are possible and resign themselves to a universe where not everything has an origin, or they argue that something, some law of physics we haven't discovered yet, prevents these loops from forming. Quantum mechanics is often invoked. The argument goes that when you try to create a bootstrap loop, quantum uncertainty steps in and disrupts it. Small errors accumulate. Information degrades. The loop destabilizes. Only perfectly self-consistent information can survive in a closed time-like curve, and perfect self-consistency might be impossible to achieve in a quantum universe. The loop collapses before it can form. The paradox is avoided not by logic but by physics, but that's speculation. We don't have experimental evidence. We don't have time machines. We don't have closed time-like curves. What we have is math that allows them and intuition that rejects them. And sitting between the math and the intuition is the Bootstrap Paradox, quietly insisting that maybe, just maybe, the universe doesn't work the way we think it does. That origin is not a requirement, that causality can be circular, that information can exist without a source, that the question "where did this come from?" might not always have an answer. The paradox also connects to deeper questions about the nature of time itself. If the Bootstrap Paradox is possible, it implies that the past and future are not separate. They're part of a single structure, a four-dimensional block where every event, past, present, and future, exists simultaneously. In that picture, time doesn't flow. It just is. You don't move through time. You exist at every moment of your life all at once, spread out across the timeline like a thread. The bootstrap loop is just one thread folded back on itself. The loop doesn't travel through time, it's embedded in time. And from the perspective of the four-dimensional block, there's nothing strange about it. It's just a closed curve, a circle drawn on a map. The circle doesn't need a starting point, it just is. That picture resolves the paradox by dissolving the concept of temporal flow. There's no movement, no progression, no unfolding, just a static structure where all events coexist. The bootstrap loop is part of that structure. It doesn't need an origin, because origins only make sense in a picture where time flows and events happen in sequence. Remove the flow, and the problem disappears. The loop is just a feature of the geometry. Strange, yes, but not paradoxical. The Bootstrap Paradox asks us to choose between two equally uncomfortable options. Either time travel to the past is impossible, in which case the paradox is just a curiosity, or time travel is possible, in which case we have to accept that the universe can contain information without origin, events without external causes, and objects that exist simply because they exist. Either way, something has to give, either our intuition about origins or our equations about time. And that brings us to a different kind of paradox, one that doesn't involve time travel at all, one that sits at the heart of quantum mechanics and asks a question that's somehow even stranger. Not can something exist without an origin, but can something exist in two contradictory states at once? Can a thing be both alive and dead, both here and there, both real and unreal until you look at it? The Bootstrap Paradox bends causality. The next paradox bends reality itself. The Bootstrap Paradox asked us to accept that something could exist without ever being created. That information could loop through time with no origin, no author, no moment of birth. It bent causality into a circle and left us staring at a closed structure where every event caused the next and nothing caused the first. Strange, uncomfortable, but at least the loop was consistent. At least the timeline made sense once you accepted that beginnings were optional. The next paradox doesn't give you that luxury. It doesn't bend causality. It breaks reality. It asks you to accept that an object, a physical thing with mass and location, can exist in two contradictory states at the same time, that something can be alive and dead simultaneously, that the universe doesn't pick a side until you force it to. And the moment you look, the moment you measure, one of those states vanishes as if it never existed. Except it did exist. The math says so. The experiments confirm it. And yet every instinct you have, every rule you learned about how objects behave, screams that this is impossible. This is Schrödinger's cat. And if you think you understand it, you probably don't. Because the paradox isn't really about a cat. It's about the gap between the quantum world, where particles play by rules that make no sense, and the everyday world where objects have definite properties and don't flicker in and out of existence when you blink. The cat is just the messenger. And the message is that reality at its most fundamental level does not behave the way reality at your level behaves. And nobody, not even the physicists who use quantum mechanics every day to design computer chips and lasers and MRI machines, can tell you why. The thought experiment was proposed by Erwin Schrödinger in March of 1935. Schrödinger was one of the founding architects of quantum mechanics, the branch of physics that describes how particles behave at the smallest scales. He'd already written the equation that bears his name, the Schrödinger equation, which governs how quantum systems evolve over time. It's one of the most important equations in all of physics. It works. It predicts the behavior of atoms, electrons, photons, everything at the quantum level with astonishing precision. But Schrödinger hated what it implied. At the time, the dominant interpretation of quantum mechanics was called the Copenhagen interpretation, championed by Niels Bohr and Werner Heisenberg. The Copenhagen view said that a quantum system doesn't have definite properties until you measure it. Before measurement, the system exists in something called a superposition, a state where all possible outcomes coexist at once. The particle is here and there, the electron's spin is up and down, the photon went through both slits. Not that we don't know which state it's in. It genuinely is, in all states simultaneously. The superposition is real. And only when you perform a measurement does the system collapse into one definite outcome. The act of observation forces the universe to pick a side. Schrödinger thought this was absurd, not the math. The math worked, but the interpretation. The idea that reality was fuzzy and indefinite until someone looked at it felt wrong. It felt like physics was smuggling in something mystical, something subjective, something that made the universe depend on observers in a way that violated the whole point of science. Science was supposed to describe an objective reality that existed independently of whether anyone was watching. The Copenhagen interpretation seemed to say the opposite, that reality wasn't real until you measured it, that the universe was, in some sense, waiting for you to look before deciding what to be. So Schrödinger designed a thought experiment to show how ridiculous this was. He wanted to take the rules of quantum mechanics, the rules that worked perfectly fine for electrons and photons, and scale them up to something large and familiar, something where the absurdity would be obvious, something where the idea of superposition would reveal itself as the nonsense he thought it was. He described it in a paper. Picture a sealed box. Inside the box is a cat, alive, healthy, sitting there. Also inside the box is a small amount of radioactive material, not much. Just enough that over the course of 1 hour there's a 50% chance that a single atom will decay. Next to the radioactive material is a Geiger counter, a device that detects radiation. The Geiger counter is wired to a hammer. The hammer is poised above a flask of poison gas, cyanide, or something equally lethal. If the atom decays, the Geiger counter clicks, the hammer falls, the flask shatters, the gas is released, and the cat dies. If the atom doesn't decay, nothing happens, the cat lives. Close the box. Wait 1 hour. Don't open it, don't peek, just wait. Now ask the question. According to quantum mechanics, what is the state of the cat? The answer, if you apply the Copenhagen interpretation consistently, is that the cat is in a superposition, both alive and dead at the same time. Because the radioactive atom is a quantum system. And until you measure it, until something interacts with it in a way that collapses its wave function, the atom exists in a superposition of decayed and not decayed. Both states are real, both are part of the atom's quantum description. And because the cat's fate is tied directly to the atom's state, The cat inherits the superposition. The cat is 50% alive and 50% dead. Not that there's a 50% chance it's alive. It is both, simultaneously. The wave function of the entire system, atom plus Geiger counter plus hammer plus flask plus cat, is a single quantum state that contains both outcomes. Then you open the box, you look inside, and the wave function collapses, the superposition resolves, the universe picks one outcome. You see a live cat or a dead cat, never both. The act of observation forces the system into a definite state. Before you looked, the cat was both. After you look, it's one or the other. And the other possibility, the one that didn't happen, vanishes, not just from your knowledge, from reality itself. It stops being part of the wave function. It's gone. Schrödinger's point was that this is obviously insane. Cats are not both alive and dead. You don't need to open the box to know that. The cat knows whether it's alive. The Geiger counter knows whether it detected a decay. The hammer knows whether it fell. The universe doesn't wait for a human to peek inside before deciding which outcome happened. The idea that a macroscopic object like a cat could exist in a superposition until observed was, in Schrödinger's words, quite ridiculous. He wasn't defending the idea, he was attacking it. He was saying, look, if you take your theory seriously, this is where it leads. And since this is absurd, maybe the theory needs to be reconsidered. The problem is that quantum mechanics refused to be reconsidered. It kept working. Every experiment confirmed the predictions. Particles really do exist in superpositions. Photons really do go through both slits in the double-slit experiment until you measure which slit they went through. Electrons really do have indeterminate spin until you measure the spin. The math was bulletproof. The predictions were flawless. And the interpretation, as strange as it was, seemed to be the only way to make sense of what the experiments were showing. So the cat stuck around. Not as a refutation of quantum mechanics, as a symbol of its strangeness. The thought experiment became one of the most famous images in all of physics, the cat in the box, alive and dead, waiting for someone to look. It's been referenced in textbooks, television shows, philosophy papers, pop culture. Everyone knows the setup. Almost no one agrees on what it means. Let's be clear about what superposition actually is, because the term gets thrown around loosely. Superposition is not the same as uncertainty. It's not that we don't know the cat's state and we're just describing our ignorance. That would be easy. That would be classical probability. Flip a coin, cover it with your hand. The coin is heads or tails. You don't know which, but it is one or the other. The coin has a definite state. You're just ignorant of it. That's not what's happening in quantum mechanics. In a superposition, the system genuinely does not have a definite state. It's not that the particle is in one place and we don't know where. It's that the particle is in multiple places at once. The wave function, the mathematical object that describes the system, contains all the possibilities simultaneously. And those possibilities interfere with each other. They affect each other. You can do experiments where the interference between the two states produces measurable effects that couldn't happen if the particle were only in one state. The superposition is real. It's not a description of our knowledge. It's a description of the system itself. The classic demonstration is the double-slit experiment. Fire a single photon at a barrier with two narrow slits. On the other side, you have a screen that detects where the photon lands. If you don't measure which slit the photon goes through, you get an interference pattern on the screen, bright bands and dark bands. The kind of pattern you only get when waves overlap and interfere with each other. But you fired one photon, one particle. What's it interfering with? The answer is itself. The photon goes through both slits at once. Its wave function splits. The two components travel different paths, recombine, interfere, and produce the pattern. One particle, two slits, both used. That's superposition. Now put a detector at one of the slits to measure which path the photon takes. The moment you do that, the interference pattern vanishes. The photon behaves like a particle that went through one slit or the other, not both. The superposition collapses. The act of measurement, the interaction between the photon and the detector, forces the photon to pick a path, and once it picks, the other possibility stops existing. The wave function collapses from a superposition of both paths to a single definite path. Measurement kills the interference. This is the measurement problem, the single biggest unresolved question in quantum mechanics. The math tells you how systems evolve when they're not being measured. The Schrödinger equation governs that. It's deterministic, smooth, predictable. The wave function spreads out, splits, interferes, does all kinds of strange things, but it evolves according to precise rules. Then you measure the system, and the wave function collapses. The superposition disappears. One outcome becomes real, the others vanish, and the collapse is sudden, discontinuous. The smooth evolution stops. The system jumps to a definite state. The measurement problem asks, what counts as a measurement? When does the collapse happen? Why does it happen? The math describes the collapse. It tells you the probabilities of each outcome. But it doesn't tell you what triggers the collapse or why one outcome is selected over another. The Copenhagen interpretation says measurement causes collapse. Fine, but what is a measurement? Does the Geiger counter count, or does it require a conscious observer? Does the cat's awareness of its own state collapse the wave function, or does it take a human opening the box? Modern physicists generally agree that consciousness is not required. The Geiger counter is enough. Any interaction that entangles the quantum system with the environment, anything that leaves a record, anything that could in principle be observed, that's enough to collapse the wave function. You don't need a person. You don't need awareness. You just need the system to interact with something large and complex enough that the quantum information gets scrambled into the environment. That process is called decoherence, and decoherence explains why macroscopic objects don't remain in superpositions. The cat interacts with air molecules, with the walls of the box, with its own internal processes. Those interactions leak information into the environment. The superposition decoheres almost instantly. Long before you open the box, the cat is either alive or dead. Not both, but decoherence doesn't solve the measurement problem. It explains why we don't see superpositions in everyday life. It doesn't explain why the wave function collapses at all. Decoherence makes the different outcomes look independent. It suppresses the interference between them. But mathematically, the superposition is still there. It's just spread out across the environment. The wave function of the entire universe still contains all the outcomes. They've just been separated in a way that makes them invisible to local observers. The collapse hasn't happened. The universe is still in a superposition. We just can't see it. That brings us to the interpretations, plural. Because there's no consensus. Quantum mechanics works. Everyone agrees on the predictions. But what the theory means, what's actually happening underneath the math, that's where physicists split into camps. The Copenhagen interpretation says the wave function is not a description of reality. It's a description of our knowledge, or more precisely, it's a tool for calculating probabilities. The collapse happens when you gain information. Before measurement, multiple outcomes are possible. After measurement, one outcome is known. The wave function updates to reflect that. It's epistemological, about knowledge, not ontological, not about what's real. And if you ask what the cat's state was before you opened the box, The Copenhagen answer is that the question is meaningless. There was no state. There was only a wave function, and the wave function contained both possibilities. The cat wasn't alive or dead. It was in a superposition, and superposition is not a state in the classical sense. It's something else, something quantum, something that doesn't map onto our everyday concepts. The many worlds interpretation takes the opposite approach. It says the wave function is real. It's the whole story. There is no collapse. When you measure a quantum system, the universe doesn't pick one outcome. It realizes all of them. The wave function branches, splits. One branch contains a live cat and a version of you who sees a live cat. Another branch contains a dead cat and a version of you who sees a dead cat. Both branches are real. Both continue forward. Both are part of the same universal wave function. You don't see the other branch because you're stuck in one branch, but it's out there, parallel, inaccessible, just as real as yours. This interpretation has a certain elegance. It takes the math seriously. The Schrödinger equation never includes a collapse term. Collapse is added by hand in the Copenhagen interpretation. Many worlds says forget the collapse. Let the wave function evolve smoothly. Let it branch. The appearance of collapse is just you losing track of the other branches. From your perspective, one outcome happened, but objectively, all outcomes happened. You're just experiencing one thread of a vastly larger reality. The cost is that you're multiplying worlds. Every quantum event with multiple possible outcomes spawns new branches. And at the quantum level, that's happening constantly, everywhere, every atom, every photon, every particle interaction. If many worlds is right, the universe is splitting into an unimaginable number of parallel branches every fraction of a second. Most physicists find that hard to swallow, not because it's logically inconsistent, it's not, but because it's extravagant. You're creating infinite realities to avoid adding one collapse rule to your equations. The cure feels worse than the disease. There are other interpretations. Pilot wave theory, developed by de Broglie and later Bohm, says particles always have definite positions. They're guided by a wave that evolves according to the Schrödinger equation. The wave is real, the particle is real. Superposition is just the wave spreading out. The particle follows one path. The wave explores all paths. Measurement reveals where the particle is. No collapse needed. The catch is that the theory is non-local. The wave in one place can instantly affect the particle somewhere else, faster than light, not in a way that lets you send signals, so relativity is safe, but in a way that makes the universe deeply interconnected in ways that feel spooky. Relational quantum mechanics says the state of a system is relative to the observer. One observer sees a superposition, another sees a definite state. Both are right. There's no absolute state. State is relational, like velocity and relativity. You can't ask how fast something is moving without specifying relative to what. Similarly, you can't ask what state a system is in without specifying relative to which observer. The cat is dead relative to the Geiger counter. Alive and dead relative to you standing outside the box. Both descriptions are valid. Reality is observer-dependent, not in a subjective, consciousness-dependent way, in a relational, frame-dependent way. Every interpretation solves the measurement problem by redefining what measurement means, or what reality is, or what the wave function describes. None of them feel fully satisfying. None of them are universally accepted. The paradox remains, not a logical contradiction, an interpretive gap. The math works. The experiments confirm the predictions, but the story we tell about what's happening underneath, that's still up for grabs. And that's what makes Schrödinger's cat so enduring. It's not a puzzle with a solution, it's a mirror. It reflects back at you whatever assumptions you're making about reality. If you think reality is definite and observer independent, the cat forces you to explain why superpositions collapse. If you think the wave function is real, the cat forces you to accept branching universes. If you think observers create reality, the cat asks you to define observer. If you think the question is meaningless, the cat asks you why the math works so well if it's not describing something. The cat sits in that box, neither alive nor dead, and it refuses to let you look away. Because this isn't just about quantum mechanics, it's about the boundary between the quantum world and the classical world. The world of particles and waves and superpositions, and the world of cats and tables and definite outcomes. We live in the classical world. We experience objects with definite properties. But the classical world is made of quantum stuff. Atoms, electrons, photons, all of them obeying quantum rules. So where's the line? At what point does quantum weirdness stop and classical normality begin? How many atoms do you need before superposition becomes absurd? How big does an object have to be before it's required to pick a state? Nobody knows. There's no sharp dividing line in the theory. The Schrödinger equation works for 1 particle, 10 particles, a billion particles. It scales. In principle, you could write down a wave function for the entire cat. It would be impossibly complicated, but mathematically it's allowed. The cat should be in a superposition. The fact that it's not, or at least the fact that we never observe it in one, is explained by decoherence. But decoherence is a practical answer, not a fundamental one. It tells you why superpositions are fragile. It doesn't tell you why reality picks one outcome. Some researchers are trying to test this. They're building experiments that push larger and larger objects into quantum superpositions. Molecules, viruses, tiny mechanical resonators. The goal is to find the boundary, to see how big you can make something before the quantum rules stop working. So far, they haven't found a limit. The bigger the object, the harder it is to isolate from the environment. Decoherence happens faster. But in principle, if you could perfectly isolate a large object, it should still obey quantum mechanics. It should still be able to exist in a superposition. The cat should still be possible. Schrödinger's cat is a paradox about measurement, about observation, about the role of the observer in determining reality. But it's also a paradox about scale, about the tension between the microscopic and the macroscopic, about why the rules that govern electrons don't seem to govern cats. And the answer, as uncomfortable as it is, might be that the rules do govern cats. We just don't see it because cats are big and warm and interact with their environment constantly. The superposition is there in the math. It's just hidden by decoherence. The wave function is still evolving smoothly. We just can't access the other branches. Reality is still fundamentally quantum. We just experience a tiny classical slice of it. If that's true, then the paradox isn't a paradox at all. It's a feature. The universe is quantum. Superpositions are real. Collapse is either an illusion or a branching or a contextual thing that depends on your frame of reference. The cat is both alive and dead. You just only ever see one. And the reason you only see one is because you're part of the system. You're entangled with the outcome. You've decatard along with the cat. The superposition didn't go away. You stopped being able to see it. You became part of one branch. And from inside that branch, it looks like the wave function collapsed. But from outside, from the perspective of the universal wave function, both branches are still there. Both cats exist. Both are real. You're just not in both places at once. That's the heart of the paradox. The universe at its smallest scales doesn't play by the rules we expect. It's not definite, it's not local, it's not even clear that it's real in the way we think of real. Particles are waves. Waves are particles. Outcomes are probabilities until you measure them. And measurement doesn't just reveal what was there, it participates in creating what's there, or splitting what's there, or selecting one thread out of many, depending on which interpretation you buy. Schrödinger wanted to show that quantum mechanics led to absurdities. He succeeded. The cat is absurd. But the universe didn't care. It kept being quantum, and we kept having to adjust our intuitions to match. The paradox remains. The cat stays in the box, alive and dead, waiting for you to decide which story you're going to tell about what happens when you open it. And no matter which story you choose, the math will keep working, the experiments will keep confirming it, and the cat will keep sitting there, silent, superposed, daring you to look. But not all paradoxes require quantum mechanics to break your brain. Some are older, much older, older than physics, older than calculus. Some paradoxes were invented by ancient Greek philosophers who had nothing but logic and geometry and a refusal to accept that motion made sense. And one of them, proposed more than 2,000 years ago, suggests that motion itself is impossible, that you cannot cross a room, that an arrow cannot reach its target, that change is an illusion, and the argument, as simple as it is, has never been fully resolved. Schrödinger's cat forced us to confront the idea that reality at its smallest scales doesn't behave the way reality at our scale behaves, that particles exist in superpositions, that measurement collapses possibilities, that the universe might be fundamentally uncertain until you look at it. Quantum mechanics breaks our intuitions about definiteness, about objects having properties whether we observe them or not. It's strange, it's uncomfortable, and it took the entire 20th century to even begin wrapping our heads around it. But not all paradoxes require quantum mechanics to make you question reality. Some are older, much older. Some were invented more than 2,000 years ago by philosophers who had nothing but logic, geometry, and an unshakable belief that the universe wasn't making sense. No particle accelerators, no calculus, no differential equations, just pure thought. And one of those ancient paradoxes, proposed by a Greek philosopher named Zeno of Elea around 450 BCE, suggests something so simple and so devastating that it's never fully gone away. It says that motion is impossible, that an arrow fired from a bow cannot reach its target, that you cannot walk across a room, that every step you take, every movement you make, is a logical impossibility. And the argument is so clean, so direct, that for more than 2 millennia, some of the greatest minds in history have had to stop and explain why it's wrong, or if it's wrong, or what wrong even means when you're talking about something as basic as motion. Zeno lived in the Greek colony of Elea, in what's now southern Italy, around the 5th century BCE. He was a student of Parmenides, a philosopher who believed that reality was singular, unchanging and eternal. Parmenides argued that change was an illusion, that plurality was an illusion, that the universe was one unified, unchanging whole, and everything we perceive as motion or transformation or multiplicity was just our senses lying to us. It was a radical position. Most people, then and now, look at the world and see things moving, changing, appearing, disappearing. Parmenides said no, that's all surface. Underneath, nothing changes. Reality is static. Motion is impossible. Zeno took it upon himself to defend his teacher's view, and he did it in the most effective way possible. He didn't argue directly for Parmenides' metaphysics. He argued against the alternative. He showed that if you assume motion is real, if you assume space and time can be divided, if you assume the common sense view that things move from one place to another, then you run into contradictions. Logical contradictions, the kind that can't be hand-waved away. Zeno formulated a series of paradoxes, thought experiments, designed to demonstrate that motion, as we think we understand it, leads to absurdity. And one of the most famous, the one that cuts deepest, is the paradox of the arrow. The setup is almost offensively simple. Picture an arrow in flight. It's been released from a bow. It's traveling through the air toward a target. You can see it moving. Everyone can see it moving. Motion is happening. Now freeze time. Pick any single instant during the arrow's flight. A snapshot, a durationless moment. At that instant, the arrow occupies a specific region of space, a region exactly equal to the arrow's length. At that instant, the arrow is not moving to where it is, because it's already there. And it's not moving to where it is not, because no time is passing during this instant for it to get anywhere. At this frozen moment, the arrow is at rest. It is motionless. It occupies a fixed position and does nothing else. So far, no problem. That's just what an instant is. A single point in time. But here's the issue. Time is made up of instants. Just like a line is made up of points, time is made up of these durationless moments. Every instant in time is like the one we just described. At every instant, the arrow is at rest. It occupies a space equal to itself. It is not moving. If at every instant the arrow is at rest, and time is nothing but a sequence of instants, then at what point does the arrow actually move? When does the motion happen? You can't point to a single instant and say, there, that's where the motion occurs, because at every instant the arrow is stationary. Motion seems to require time to pass, but time doesn't pass during an instant. An instant has no duration, so motion can't happen during an instant. And if motion can't happen during any instant, and time is just a collection of instants, then motion can't happen at all. The arrow is always at rest. It never moves, and yet we see it move. Contradiction. Zeno wasn't saying arrows don't hit targets. He wasn't denying the evidence of his senses. He was saying that our conceptual framework for understanding motion is broken. That the way we think about time and space and movement leads to logical impossibilities. And if our logic leads to impossibilities, then either our logic is wrong or our assumptions about reality are wrong. Parmenides said reality is unchanging. Zeno said, if you disagree, explain the arrow. Explain how motion is possible when at every moment nothing is moving. The paradox stuck. It bothered people. Aristotle spent significant time trying to refute Zeno. His response, roughly, was that Zeno was confusing two different kinds of infinity. Aristotle distinguished between potential infinity and actual infinity. Potential infinity is the idea that you can keep dividing something forever. You can always find a smaller interval, a thinner slice, a more precise measurement, but you never complete the division. It's an ongoing process. Actual infinity is the idea that the division is complete, that time is actually composed of infinitely many discrete instants, all laid out, all existing simultaneously. Aristotle said Zeno was treating time as if it were actually divided into instants, but time isn't like that. Time is continuous. It's a smooth flow. You can divide it conceptually, sure, but the divisions aren't real. Motion happens across intervals, not at instants. An arrow moves during a span of time, not at a point in time. Asking what the arrow is doing at a single instant is like asking what color the number 7 is. It's a category mistake. Motion is a property of intervals, not of points. That response has a certain appeal. It shifts the problem by redefining what time is, but it doesn't fully resolve the paradox. Because even if time is continuous, you can still talk about instants. You can still ask what the arrow's state is at a specific moment, and at that moment, the arrow occupies a specific location. It's not occupying two locations, it's not in between locations, it's at one place. And if it's at one place, it's not moving. Aristotle's answer feels like it's dodging the question. Yes, motion happens over intervals, but intervals are made of points, and at each point, the arrow is at rest. So how does adding up a bunch of rest points give you motion? How does static plus static equal movement? For more than 1,000 years, that question sat there. Philosophers debated it, mathematicians worked around it, but nobody had a clean answer. Not until the 17th century. Not until Isaac Newton and Gottfried Wilhelm Leibniz, working independently, invented calculus. And calculus didn't just answer Zeno's paradox, it demolished it. It showed that the intuition behind the paradox, the idea that motion at an instant is impossible, was based on a misunderstanding of how infinity works. Specifically, it was based on the assumption that if you add up infinitely many things, you get infinity. That if time is made of infinitely many instants, and the arrow is at rest at each instant, then the total motion is zero. But that assumption is wrong. The sum of infinitely many, infinitesimally small things can be finite. In fact, that's the entire foundation of calculus. And once you understand that, Zeno's paradox unravels. Here's how it works. Imagine the arrow's flight. It starts at position 0. After some time, it's at position 10 meters. You want to know its velocity at some instant during that flight. Velocity is change in position divided by change in time. Over the whole flight, if it took 1 second, the average velocity is 10 meters per second. Fine. But what about the velocity at a specific instant? At that instant, no time passes. The change in time is 0. The change in position is also 0. The arrow is at one spot. Dividing 0 by 0 gives you nothing useful. That's Zeno's problem. Motion at an instant seems undefined. Calculus solves this by using limits. Instead of asking what happens at the instant, you ask what happens as you get closer and closer to the instant. You look at smaller and smaller intervals around that moment. Say the arrow is at position 10 meters at time 1 second. A tiny bit earlier, at time 0.999 seconds, it was at position 9.999 meters. A tiny bit later, at time 1.001 seconds, it's at position 10.001 meters. Calculate the average velocity over those tiny intervals. As the intervals shrink, the average velocity approaches a specific value. That value is the instantaneous velocity. It's the limit of the average velocity as the time interval approaches 0. The derivative, the rate of change of position with respect to time. And that derivative is a finite number. It's not 0, it's not undefined, it's the arrow's speed at that instant. This is the AT-AT theory of motion. Motion isn't something that happens at an instant. It's something that describes the relationship between different instants. An object is in motion at a given instant if it occupies different positions at different nearby instants. The arrow is moving at time 1 second because at time 0.999 seconds it was somewhere else, and at time 1.001 seconds it will be somewhere else. The motion is encoded in the trajectory, the function that maps time to position. At any single instant, the arrow is at a specific location, but the fact that it's moving is expressed by the fact that its location changes as time changes. Motion is a property of the curve, not of a single point on the curve. You can have a well-defined instantaneous velocity even though the arrow doesn't move during the instant, because velocity isn't defined by what happens during the instant. It's defined by how position changes across instants. That distinction is subtle but crucial. Zeno assumed that if the arrow is at rest at each instant, then it's not moving. Calculus says no. Being at rest at an instant means the arrow occupies one position at that instant. But the arrow can still have a velocity at that instant, defined as the rate at which its position is changing. The velocity is a property of the trajectory, a derivative, a limit. It's not a property of the single instant in isolation. The arrow doesn't need to move during an instant for it to be in motion at that instant. Motion is relational. It's about how different moments connect to each other, not about what's happening inside a single moment. Newton and Leibniz didn't solve Zeno's paradox by arguing with his logic. They solved it by building a mathematical framework that made the paradox irrelevant. They showed that you can have a rigorous, consistent theory of motion that handles instants and infinity without running into contradictions. Calculus works. It predicts the behavior of moving objects with extraordinary precision. Engineers use it to design bridges and rockets. Physicists use it to describe everything from planetary orbits to quantum fields. The fact that calculus works is proof that motion is mathematically coherent. Zeno's paradox was based on the assumption that motion at an instant is logically impossible. Calculus shows that the assumption was wrong. Motion at an instant is not only possible, it's calculable. You can write down an equation for it. You can measure it. You can use it to build things. The arrow moves. The math explains how. Case closed. Except not everyone agrees the case is closed. Because calculus solves the mathematical problem, but it doesn't necessarily solve the philosophical problem. Yes, you can define instantaneous velocity using limits and derivatives, but what is that velocity? Is it a real property of the arrow at that instant? Or is it just a convenient mathematical abstraction, a shorthand for describing how the arrow's position changes over a span of time? When you say the arrow has a velocity of 10 meters per second at time 1 second, are you saying something about the arrow at that instant? Or are you saying something about the arrow's trajectory in the neighborhood of that instant? The math works either way, but the interpretation matters, and philosophers are still arguing about it. There's also the question of whether space and time are actually continuous. Calculus assumes they are. It assumes you can zoom in on any interval and find smaller intervals, that you can take limits as intervals shrink to zero, that there's no smallest unit of space or time. But what if that's wrong? What if space and time are fundamentally discrete? What if there's a smallest possible distance, a smallest possible duration, and you can't subdivide further? That's not just a wild speculation. Some approaches to quantum gravity, theories that try to unify quantum mechanics and general relativity, suggest that space-time might be quantized at the Planck scale. The Planck length is about 10 to the negative 35 meters. The Planck time is about 10 to the negative 44 seconds. If space-time is discrete at that scale, then Zeno's paradox comes roaring back. Because now time really is made up of indivisible instants, and at each instant the arrow is at a specific location. And if the arrow is at a specific location at each instant, and instants are discrete, then motion is not a smooth, continuous process. It's a series of quantum jumps from one position to the next. The arrow doesn't glide through space, it teleports. Tiny teleports, too small to detect, but teleports nonetheless. And if that's what motion actually is, then Zeno was right. Motion as we think of it, smooth, continuous change, is an illusion. What we call motion is actually a sequence of static states, stitched together so finely that we can't see the gaps. That's speculative. We don't know if space-time is quantized, but the possibility keeps Zeno's paradox alive. Because if space and time are fundamentally discrete, then calculus, for all its power, is just an approximation. A useful tool that works at large scales but doesn't describe the underlying reality. The arrow doesn't actually have an instantaneous velocity. It has a sequence of positions at a sequence of discrete moments, and velocity is just the average change between those moments. Zoom in far enough, and the smooth curve breaks down into a pixelated staircase. And at that level, Zeno's logic holds. At each discrete moment, the arrow is motionless. The motion is just the illusion created by flipping through the frames fast enough. Bertrand Russell, the mathematician and philosopher, thought deeply about Zeno's paradoxes and wrote about them extensively. He pointed out that the paradox reveals a deep tension between our intuitive sense of motion and the way motion is described mathematically. He said that in calculus, motion is never actually happening at an instant. The arrow is at one place at one time and at another place at another time. The change of position occurs between the instants, not at any instant. But then, when does it occur? If it doesn't happen at any instant, and time is just a collection of instants, when does the change take place? Russell admitted this was philosophically troubling. He said the paradox forces us to accept that motion is a kind of miracle, not a supernatural miracle, but a conceptual one. Something that happens without happening at any particular time. The arrow is here, then it's there, and the transition is not located at any point in time. It's spread across time. It's a property of the interval, not of the moments within the interval. That idea, strange as it sounds, is actually how modern physics treats motion. In relativity, space-time is a four-dimensional structure. Time is a dimension, not fundamentally different from space. Your entire life, from birth to death, exists as a single object in space-time called a world line, a curve traced through four-dimensional space. At any point on that curve, you have a specific position in space and a specific moment in time. You're not moving at that point, you're just there. But the world line itself encodes motion. The curve has a direction, a tangent, a four-velocity. The motion is a property of the curve, not of the individual points. In that picture, Zeno's paradox dissolves because motion is not something that happens at a moment. It's something that describes how moments are connected. The arrow's world line is a curve through space-time. At each event on that curve, the arrow is at a specific location at a specific time. The fact that it's moving is expressed by the fact that the curve extends through time. Motion is built into the geometry of space-time itself, but that still doesn't explain what motion feels like. Why we experience change as a dynamic unfolding process rather than a static four-dimensional structure. If the world line is just sitting there, complete and unchanging, why does it feel like time is flowing? Why does it feel like the arrow is moving rather than just existing as a curve? That's the problem of temporal experience, and it's related to Zeno's paradox in a deep way, because Zeno's paradox is ultimately about the gap between our lived experience of motion and the logical structure of motion. We feel motion as continuous change. We experience the arrow flying through the air. But when we try to analyze that experience, when we break it down into instants and ask what's happening at each instant, the motion vanishes. We're left with a sequence of static snapshots. And calculus, for all its power, doesn't restore the dynamism. It just gives us a way to calculate how the snapshots relate to each other. The feeling of motion, the experience of change, is something calculus describes but doesn't explain. Zeno's paradoxes, and the paradox of the arrow in particular, have been discussed and debated for more than 2,000 years. Aristotle tried to refute them. Medieval philosophers wrestled with them. Newton and Leibniz provided mathematical tools that resolved the technical issues. Modern physicists use those tools every day without giving Zeno a second thought. And yet the paradox persists, not as a practical problem. We know motion is real. We know how to describe it mathematically. We know how to predict it, measure it, control it. But as a philosophical problem, as a conceptual puzzle, the paradox is still there, because it asks a question that doesn't have a purely technical answer. It asks what motion is, not how to calculate it, what it is. And that question touches on the nature of time, the nature of change, the relationship between the continuous and the discrete, and the gap between mathematical models and lived experience. Zeno didn't have calculus. He didn't have relativity. He didn't have quantum mechanics. He just had logic and a refusal to accept that motion made sense. And the fact that his paradox is still worth talking about, still worth teaching, still worth thinking about, tells you something important. It tells you that some questions don't get answered by better math. They get reframed. They get worked around. They get embedded into new frameworks where the original problem looks different, but the question itself, the deep conceptual question, doesn't go away. The paradox of the arrow is a challenge to our intuitions about continuity. It says that if you zoom in far enough on any motion, you find stillness. That motion is made of motionlessness the way a line is made of points. And that bothers us because it feels like you're building something dynamic out of static parts. How does that work? How does adding up a bunch of nothings give you something? How does a sequence of frozen frames produce the experience of flow? Calculus gives you the tools to do the calculation. Philosophy asks whether the calculation captures what's really happening. And physics says maybe the question is wrong. Maybe motion isn't something you build out of instants. Maybe motion is fundamental, and instants are just a way we slice it up for analysis. Maybe the arrow is always moving, and the idea that it's at rest at any instant is a convenient fiction we use to make the math work. There's no consensus, but there is a lesson. The lesson is that reality at its most basic level doesn't necessarily match our intuitions. We think of motion as smooth, continuous change. We think of time as a flow. We think of space as something you can divide forever. But when you push those ideas, when you really examine them, they start to fracture. The smooth curve turns out to be made of points. The flow turns out to be a sequence of states. The continuity turns out to rest on limits and derivatives and mathematical abstractions that don't correspond to anything you can point at in the world. Zeno saw that tension. He exploited it. He turned it into a paradox. And the paradox has been forcing us to refine our concepts ever since. Zeno's paradoxes are often taught as historical curiosities, ancient philosophy, solved problems, but they're more than that. They're live issues in the foundations of physics and mathematics. They're reminders that the tools we use to describe reality, tools like calculus and geometry and logic, are human constructions, powerful constructions, useful constructions, but constructions nonetheless. And sometimes those tools smooth over gaps that are still there underneath. The gap between the discrete and the continuous. The gap between the mathematical and the experiential. The gap between what the equations say and what the equations mean. And that brings us to another kind of gap. A gap that's not about motion or time or ancient philosophy. A gap about information, about what happens when something falls into a place where the usual rules stop working, where the past gets erased, where information, the most fundamental thing in the universe according to quantum mechanics, seems to vanish without a trace. That's not a paradox about instants or arrows or how many slices you can cut time into. It's a paradox about black holes, about event horizons, about whether the universe keeps track of what falls in, or whether some things are truly lost forever. And if information can be destroyed, if the universe can forget, then everything we think we know about the laws of physics might be wrong. Zeno asked whether motion was possible if every instant contains only stillness. Calculus provided the math. Relativity provided the geometry. Neither one fully resolved the feeling that something was missing, the gap between the static and the dynamic, between the description and the experience. But at least motion, for all its conceptual slipperiness, is something we can see, something we can measure, something we can predict with extraordinary precision. The paradoxes of motion are philosophical more than physical. The universe keeps moving whether we understand how or not. The next paradox is different. It's not about motion, it's about information. And it's not a thought experiment dreamed up by ancient philosophers with too much time on their hands. It's a real, modern, actively debated crisis in the foundations of physics. A crisis that emerged in the 1970s when Stephen Hawking, one of the greatest physicists of the 20th century, discovered something about black holes that should not have been possible. Something that violated one of the most sacred principles in all of quantum mechanics. And 50 years later, despite enormous effort, despite breakthroughs that looked like solutions, despite claims that the problem is solved, the paradox is still there. Quieter now, more technical, but unresolved in ways that matter. This is the black hole information paradox. And it asks a question that sounds simple, but cuts to the heart of everything. If you throw something into a black hole, and the black hole eventually evaporates, what happens to the information about what you threw in? Does it come back out? Does it stay trapped? Does it vanish? And if it vanishes, if information can be destroyed, then quantum mechanics is wrong. Not approximately wrong. Not wrong in some edge case. Fundamentally, catastrophically wrong. The entire structure collapses. Every prediction, every experiment, every piece of technology built on quantum principles, all of it rests on a foundation that black holes appear to violate. That's not hyperbole, that's the stakes. Let's start with what a black hole is, because the popular picture, the image of a cosmic vacuum cleaner sucking everything in, is misleading. A black hole is not a hole, it's not empty space. It's a region of space-time where gravity is so strong that nothing, not even light, can escape once it crosses a boundary called the event horizon. The event horizon is not a physical surface, it's not made of anything. It's a point of no return, a one-way membrane in space-time. Cross it, and every path forward leads inward. There is no outward. The future direction, the only direction time flows, points toward the center, toward the singularity. Escape is not difficult. Escape is geometrically impossible. The structure of space-time itself forbids it. Black holes are predicted by general relativity, Einstein's theory of gravity. The equations allow for solutions where mass is compressed into such a small volume that space-time curves back on itself. If you pack enough mass into a small enough region, the escape velocity exceeds the speed of light. And since nothing can move faster than light, nothing escapes. The first exact solution describing a black hole was found by Carl Schwarzschild in 1915, just months after Einstein published the field equations. Schwarzschild was serving in the German army during World War I, and he derived the solution while recovering from an illness that would kill him shortly after. He sent the paper to Einstein, who presented it to the Prussian Academy of Sciences. The solution described a perfectly spherical, non-rotating black hole, a mathematical object. Nobody thought they were real. Decades passed, evidence accumulated. Observations of certain binary star systems showed invisible companions pulling on visible stars, companions too massive to be anything but collapsed objects. In the 1960s and 70s, astronomers detected X-ray sources in the sky that matched the predicted signature of matter spiraling into a black hole, heating up to millions of degrees as it fell. By the 1990s, observations of stars orbiting the center of the Milky Way revealed an invisible object weighing 4 million times the mass of the Sun, sitting in a region smaller than our solar system. Sagittarius A star, a supermassive black hole, real, confirmed, undeniable. Black holes exist, and once you accept that, the next question is what happens to things that fall in. The naive answer is they're gone, crushed, lost. The singularity at the center, where the curvature of space-time becomes infinite, is a place where the known laws of physics break down. General relativity predicts it. General relativity also admits it has no idea what happens there. The equations blow up, infinities appear, the theory stops working. But from the outside, from the perspective of someone far away, the object that fell in just vanishes. It crosses the event horizon and stops sending signals. The outside universe never sees it hit the singularity. It just sees the object freeze at the horizon, its light redshifting into invisibility, and then nothing. The black hole gains a little mass. That's it. The information about what fell in, its composition, its structure, its quantum state, all of that seems to disappear behind the horizon. Sealed off, inaccessible, effectively erased. That picture held for a long time. Black holes were information traps. Once something fell in, it was gone. No way out, no way to retrieve what was lost. The event horizon was a one-way street, and the singularity was the end of the road. Then in 1974, Stephen Hawking published a paper that changed everything. He applied quantum mechanics to the region just outside the event horizon and discovered that black holes are not perfectly black. They glow. They emit radiation, not much. A black hole, the mass of the Sun, would emit radiation at a temperature of about 60 nanokelvins, far colder than the cosmic microwave background. But the radiation is there, and it carries energy, and energy means mass, which means the black hole is losing mass. Slowly, incredibly slowly, but inevitably. A black hole does not last forever. It evaporates. Hawking radiation arises from quantum effects in curved spacetime. In empty space, quantum mechanics allows for the spontaneous creation and annihilation of particle-antiparticle pairs, virtual particles. They pop into existence, exist for a tiny fraction of a second, and then annihilate each other. Normally, this has no observable effect. The particles are virtual. They don't last. But near the event horizon of a black hole, something strange happens. One particle of the pair can fall into the black hole while the other escapes. The escaping particle becomes real. It carries energy away from the black hole. To an outside observer, it looks like the black hole is radiating particles. The energy for those particles comes from the black hole's mass. The black hole shrinks. Over an unimaginably long timescale, longer than the current age of the universe by many orders of magnitude for a stellar mass black hole, the black hole radiates away all its mass and disappears. It evaporates completely, nothing left, just the radiation. That's a remarkable discovery on its own. But Hawking noticed a problem. The radiation he calculated was thermal. It had a temperature, yes, but it was completely random. It carried no information about what had fallen into the black hole. A black hole formed by collapsing neutron stars would emit the same Hawking radiation as a black hole formed by collapsing hydrogen gas. A black hole that swallowed a library would emit the same radiation as one that swallowed an equivalent mass of rocks. The radiation was a perfect black body spectrum, featureless. The information about the black hole's contents was not encoded in the radiation. It was just gone. Here's where the paradox bites. Quantum mechanics has a foundational principle called unitarity. It says that information is never lost, ever. A quantum system evolves according to the Schrödinger equation, and that evolution is reversible. If you know the state of a system at one time, you can in principle calculate its state at any other time, forward or backward. The total information content of the universe is conserved. You can scramble it, spread it out, hide it in correlations, but you cannot destroy it. Unitarity is not optional. It's not a suggestion. It's built into the mathematical structure of quantum mechanics. Every experiment ever performed confirms it. Every quantum process we've observed respects it. If unitarity is violated, quantum mechanics is wrong. Black holes, according to Hawking's calculation, violate unitarity. You throw a book into a black hole. The black hole evaporates. The radiation that comes out is thermal, featureless, containing no information about the book. The information is gone, destroyed, erased from the universe. That's a direct violation of unitarity. It says that quantum mechanics does not hold in the presence of black holes, and if quantum mechanics does not hold near black holes, then we have a serious problem, because quantum mechanics is supposed to be fundamental. It's supposed to describe all physical processes at the microscopic level. If it breaks down near event horizons, then we need a new theory, a theory of quantum gravity, a theory that unifies general relativity and quantum mechanics, and we don't have that theory, not yet. The paradox is this: general relativity says black holes can form and evaporate. Quantum mechanics says information cannot be destroyed. Both theories are extraordinarily successful in their own domains. Both make predictions that have been tested to incredible precision, but they give contradictory answers about what happens to information in a black hole. One of them has to be wrong, or both of them are incomplete, or something deeper is going on that neither theory captures. For decades, this was an open wound in theoretical physics. Hawking himself initially believed information was lost. He argued that general relativity was the more fundamental theory in this context, and quantum mechanics would have to give. The event horizon was a real boundary. Information that crossed it was gone. Unitarity was violated. The universe could forget. Other physicists disagreed, loudly. The debate became one of the most intense in the field. Leonard Susskind, a theoretical physicist at Stanford, became one of the most vocal opponents of information loss. He argued that unitarity was non-negotiable. If the calculation said information was lost, the calculation was wrong, not because of a mathematical error, because it was missing something. Some mechanism, some process, some feature of quantum gravity that we hadn't discovered yet. The information had to come out. The universe had to remember. The first major shift came in the 1990s with the development of the holographic principle. The idea emerged from work on black hole thermodynamics and string theory. Jacob Bekenstein had shown in the 1970s that black holes have entropy, a measure of the amount of information or disorder in a system. The entropy of a black hole is proportional to the area of its event horizon, not its volume. That was strange. Entropy usually scales with volume. The number of ways you can arrange the particles inside a box grows with how big the box is. But for black holes, it grows with the surface area. Gerhard Hooft and Leonard Susskind developed this into the holographic principle, which says that all the information contained in a volume of space can be encoded on the boundary of that space. The three-dimensional interior is a projection of two-dimensional data on the surface. Reality is a hologram. Applied to black holes, the holographic principle suggests that the information about everything that falls into a black hole is not lost. It's encoded on the event horizon. The horizon is not a smooth, featureless surface. At the quantum level, it's a structure that stores information. When the black hole evaporates, the information is released with the Hawking radiation, not in an obvious way, not in a way you could easily decode, but it's there, encoded in subtle correlations between the particles. The radiation is not perfectly thermal, it's only approximately thermal. At a deeper level, it carries information, it remembers. This was a conceptual breakthrough, but it didn't provide a detailed mechanism. It didn't show how the information gets out. It didn't resolve the apparent conflict between general relativity, which says nothing escapes the horizon, and quantum mechanics, which says information must escape. It just asserted that somehow the information is preserved. The holographic principle became a guiding idea, a signpost pointing toward a resolution, but not the resolution itself. In 2004, Hawking conceded, sort of. He published a paper saying he was wrong about information loss. He presented an argument based on the ADS-CFT correspondence, a powerful result in string theory that relates a gravitational theory in a higher dimensional space to a quantum field theory on the boundary of that space. In this framework, the information is clearly preserved on the boundary, which implies it must be preserved in the bulk. Hawking argued that quantum fluctuations of the event horizon, tiny jitters in the geometry caused by quantum effects, could allow information to leak out. He didn't provide all the details, he didn't show exactly how, but he publicly stated that information is not lost, and he paid off a bet he'd made with John Preskill, another theoretical physicist who had argued for information conservation. The payout was an encyclopedia. Preskill requested one on baseball. Hawking gave him one on cricket. The concession made headlines, but it didn't end the debate. Conceding that information is preserved is not the same as showing how it's preserved. And without a detailed mechanism, without a calculation that tracks the information from the interior of the black hole to the outgoing radiation, the paradox remained. You need to show the path. You need to demonstrate that the Hawking radiation, when analyzed correctly, contains all the information about what fell in. And for years, nobody could do that. The next big step came in 2019. A group of researchers working on quantum gravity in certain simplified models discovered something called the island formula. They were studying black holes in a theoretical setup called anti-de Sitter space, a kind of curved spacetime that's mathematically simpler than the real universe, but captures essential features of gravity and quantum mechanics. They recalculated the entropy of the Hawking radiation, the amount of information it carries, and they found that at late times, after the black hole has been evaporating for a while, the entropy follows a curve called the Page curve. Named after physicist Don Page, the Page curve describes how the entropy of the radiation should behave if information is conserved. It starts at zero, rises as radiation is emitted, peaks when about half the black hole has evaporated, and then decreases back towards zero as the last bits of the black hole disappear. The decrease is the key part. It means the radiation is becoming more and more correlated with the interior. The information is escaping. The island formula showed that there are regions inside the black hole, called islands, that are quantum mechanically connected to the radiation outside. The information in the island is effectively the same as the information in the radiation. The island grows as the black hole evaporates, eventually encompassing the entire interior. When the black hole is gone, all the information has transferred to the radiation. The page curve is recovered. Information is conserved. The paradox in this setup is resolved. This was a huge advance. In 2020, the result was widely celebrated as a solution to the information paradox. Papers were published, talks were given. The consensus in the community shifted strongly toward information being preserved. But there are caveats, big ones. The island formula works in specific models that are simpler than the real universe. Models where space-time has different properties, where certain approximations hold, where the math is tractable. Whether the same mechanism works in our universe with our black holes is still an open question. The calculation hasn't been done in full generality. It might not be possible to do it without a complete theory of quantum gravity. And we don't have that theory. There are other proposed resolutions, each with its own strengths and problems. The fuzzball proposal, developed by Samir Mathur and collaborators, suggests that the event horizon is not a smooth, empty surface, but a dense tangle of strings and quantum degrees of freedom. The interior of the black hole, in this picture, is not empty space leading to a singularity. It's a highly excited quantum state, a fuzzball, that extends all the way out to where we think the horizon is. Information is stored in the structure of the fuzzball. When the black hole evaporates, the fuzzball shrinks and the information is released. There's no information loss because the information was never behind a true event horizon. The horizon is an illusion, an effective description of a much more complex quantum object. The firewall paradox, proposed by Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully in 2012, takes a different approach. They argued that if information is preserved, then the Hawking radiation must be maximally entangled with the interior of the black hole. But quantum mechanics forbids a particle from being entangled with two different systems at once. The radiation is also entangled with the radiation that was emitted earlier. That's a contradiction. The resolution, they suggested, is that the smooth, empty space we expect just inside the event horizon doesn't exist. Instead, there's a firewall, a region of ultra-high energy particles that would incinerate anything trying to cross the horizon. This preserves information, but at the cost of violating the equivalence principle, one of the foundational ideas of general relativity. The equivalence principle says that freely falling observers shouldn't notice anything special when crossing the horizon. A firewall would definitely be noticeable. You'd be vaporized. So either information is lost, or the equivalence principle is violated, or something else is wrong with our understanding. Pick your poison. Some physicists have explored the idea of information escaping through quantum tunneling. In the early 2000s, Molik Parekh and Frank Wilczek showed that when you account for the energy of the outgoing Hawking radiation, the effective geometry near the horizon changes slightly. The barrier that traps information inside becomes permeable. Particles carrying information can tunnel through. The radiation is not perfectly thermal, it's slightly correlated with the interior. Over time, as the black hole evaporates, the information leaks out. This mechanism doesn't require exotic new structures or violations of general relativity. It just requires careful accounting of quantum effects in a dynamical spacetime. It's elegant. It might even be right. But like the other proposals, it's not universally accepted. The details are subtle, and not everyone agrees the calculation holds up. There's also the possibility that information escapes through microscopic wormholes connecting the interior of the black hole to distant regions of space-time. In some models, the entanglement between the Hawking radiation and the black hole interior can be interpreted geometrically as wormholes. These wormholes are not traversable. You can't use them to send messages or travel faster than light. But they provide a quantum connection that allows information to be shared. The island formula, in fact, can be interpreted in terms of these wormhole connections. The islands are regions connected to the exterior by quantum threads. The information doesn't escape by crossing the horizon in the usual sense. It's already outside, connected through the geometry of entanglement. This is a deeply strange picture. It blurs the line between interior and exterior, between here and there, but it's consistent with the math. The current consensus, if you can call it that, is that information is probably preserved. Most physicists working on quantum gravity believe the paradox has been resolved in principle, even if the details are still being worked out. The page curve calculation in simplified models is convincing evidence that the right answer involves information escaping with the radiation. The holographic principle provides a framework for understanding how that's possible. The various mechanisms, fuzzballs, firewalls, tunneling, wormholes, are different attempts to fill in the picture. None of them are complete. None of them are universally accepted. But the tide has shifted. Information loss is no longer the favored position. Unitarity wins, quantum mechanics holds, but there's still something unsettling about the whole situation. Because the resolution, whatever it turns out to be, requires black holes to behave in ways that violate our intuition about what an event horizon is. If information escapes, then the horizon is not a perfect seal. Something is leaking out. Either the horizon is not smooth, or it's not empty, or it's not really there in the way we thought. The classical picture of a black hole, a region of space-time with a well-defined boundary that nothing can cross, is wrong, or at least incomplete. The quantum picture is stranger, fuzzier, more interconnected. The black hole is not a local object, it's entangled with its surroundings. Its interior is not separate from the radiation it emits. The distinction between inside and outside breaks down when you account for quantum mechanics properly. That's a profound shift. It means general relativity, for all its success, is missing something. The event horizon is not the absolute boundary the classical theory says it is. Quantum effects soften it, blur it, allow information to pass through in ways that classical geometry forbids. And that's a clue that the final theory of quantum gravity, the theory that unifies relativity and quantum mechanics, will describe space-time in a fundamentally different way. Not as a smooth fabric, but as something quantum, something discrete, something where the geometry itself is emergent from deeper quantum information. The information paradox is not just about black holes, it's about the nature of reality. It's about whether the universe keeps track of everything that happens, or whether some things can be truly erased. It's about whether the past is recoverable, whether the present contains enough information to reconstruct everything that led to it. And the answer seems to be yes. The universe remembers. Information is not lost. But the mechanism by which it remembers is so strange, so far removed from our everyday experience, that we're still trying to wrap our heads around it. And that brings us to another kind of strangeness. One that doesn't require black holes or quantum gravity or the distant future when black holes evaporate. One that happens right here in our solar system with technology we've already built. One that involves twins, clocks, and the simple act of moving very fast. Because if black holes distort space to the point where time stops at the horizon, Ordinary motion does something almost as strange. It stretches time. It makes clocks run at different rates. It allows one twin to age slower than the other, not through magic or trickery, but through the structure of space-time itself. The paradox there isn't about information, it's about time, and it asks a question that's somehow even more personal. If time is relative, if your clock and my clock can disagree, then which one of us is right? And what does that say about the nature of now? The information paradox left us staring at black holes and wondering whether the universe keeps track of everything or whether some things can be truly erased. The consensus now leans toward preservation. Information survives. The universe remembers. But the mechanism is so strange, so tangled up in quantum entanglement and holographic principles and the fuzzy boundary between inside and outside, that we're still working out the details. Black holes don't let go easily. When they do, when information escapes with the Hawking radiation, it comes out scrambled, encoded, hidden in correlations so subtle that untangling them might take longer than the age of the universe itself. But you don't need a black hole to make time behave strangely. You don't need an event horizon or a singularity or a region where space-time curves so sharply that the future points inward and escape becomes geometrically impossible. You just need speed, ordinary motion. The kind of motion we understand, the kind we can engineer, the kind we've already achieved with satellites and rockets and particle accelerators. Because, according to Einstein's theory of special relativity, published in 1905, time is not absolute. It's not a universal clock ticking at the same rate for everyone everywhere. Time is relative. It depends on how fast you're moving. And if you move fast enough, your clock runs slower than mine. Not because your clock is broken, because time itself is running slower for you. You age less. You experience less. The universe waits for you while you race through it. And when you come back, when you stop and compare notes, you'll find that less time has passed for you than for everyone who stayed still. That's not a metaphor. It's not an optical illusion or a measurement artifact or something that only shows up in equations. It's real. It's measurable. It's been confirmed in experiment after experiment for more than a century. And it leads directly to one of the strangest thought experiments in all of physics. A scenario so simple you can explain it to a child, and so unsettling that it's been argued about, analyzed and picked apart by physicists since the day Einstein first described it. It's called the twin paradox, and the question it asks is this: if you have two identical twins, and one of them gets on a spaceship and flies away at close to the speed of light while the other stays on Earth, and then the traveling twin comes back, which one is younger, and why? The setup is clean. Start with two twins, call them Stella and Terra. They're born on the same day, same age, same biology, same everything. Terra stays on Earth, lives a normal life, works, eats, sleeps, watches time pass at the usual rate. Stella gets on a spaceship, a fast one. Let's say it accelerates to 86.6% the speed of light. That's a specific number for a reason. At that speed, the Lorentz factor, the mathematical term that describes how much time dilation occurs, is exactly 2. For every year that passes on the spaceship, 2 years pass on Earth. Stella flies to a nearby star. Let's say it's 12 light-years away. At 86.6% of light speed, the trip takes a bit less than 14 years from Earth's perspective. Stella turns around and comes home at the same speed. Another 14 years. Total elapsed time on Earth, 28 years. Terra is now 28 years older than when Stella left. But from Stella's perspective, time was running slower. Her clock, her heartbeat, her cellular aging, All of it was ticking at half the rate of Terra's. The outbound trip felt like 7 years to her. The return trip, another 7. Total time experienced by Stella, 14 years. She steps off the spaceship. She's aged 14 years. Terra has aged 28. Stella is now 14 years younger than her twin. Not in appearance, not subjectively. Actually younger, biologically, measurably. Her cells have divided fewer times. Her neurons have fired fewer signals. She has lived through fewer seconds of subjective experience. Terra is 43 years old. Stella is 31. That's not controversial. That's the prediction of special relativity, and it's been tested and confirmed in ways we'll get to in a moment. The paradox comes in when you think about the symmetry, because from Stella's point of view, she was the one sitting still in the spaceship while Terra and the entire Earth were moving away from her at 86.6% of light speed. Special relativity says all inertial motion is relative. There's no absolute rest, no preferred frame. If Stella sees Terra moving, then Terra's clock should be running slow from Stella's perspective. And if Terra sees Stella moving, then Stella's clock should be running slow from Terra's perspective. Both should see the other aging slower. When they reunite, each one should be younger than the other. That's a contradiction. Both twins can't be younger. Someone has to be objectively older when they meet. The paradox asks, which one? And how does the universe decide? The answer is that the situation is not actually symmetric. Stella and Terra are not doing the same thing. Terra stays in one inertial reference frame the entire time. She's on Earth. The Earth is moving, sure, orbiting the sun orbiting the galaxy moving through space, but none of that matters. What matters is that Terra doesn't accelerate. Her frame of reference is consistent. She's at rest relative to herself the entire time. Stella, on the other hand, does not stay in one frame. She accelerates when the spaceship launches. She's in one inertial frame during the outbound journey. Then she turns around. That turnaround involves acceleration. Deceleration, actually, and then acceleration in the opposite direction. During the turnaround, she switches from one inertial frame to a completely different one. Then she's in a new inertial frame on the way home, and when she arrives, she decelerates again. Stella occupies multiple frames. Terra occupies one. That asymmetry is what breaks the paradox. Stella is the one who ages less because she's the one who accelerated. Some physicists will tell you that's the answer. The acceleration is what matters. It's the physical difference between the two twins. Acceleration is absolute in a way that velocity is not. You can feel acceleration. It pushes you back into your seat. It creates forces. Stella feels those forces during launch, during the turnaround, during landing. Terra feels nothing. The universe knows who accelerated. That's not a perspective thing, that's measurable. And the one who accelerated is the one who ages less. Other physicists will tell you that's not quite right. That focusing on the acceleration is misleading. That the real reason Stella ages less has nothing to do with the forces she felt and everything to do with the paths the two twins took through space-time. In special relativity, space-time is a four-dimensional structure, 3 dimensions of space, 1 of time. Your life is a curve through that structure, a path called a world line. The length of your world line, measured in a specific way called proper time, is the amount of time you experience, the amount you age. Terra's world line is a straight line through space-time. She stays in one place in space and moves forward through time. Straight path. Stella's world line is not straight. She moves through space. Her path bends. She travels out, turns around, comes back. In spacetime, that's a curved path. And here's the key. In spacetime, the straight path between two events is the longest. That's the opposite of how it works in ordinary space. In ordinary space, the straight line between 2 points is the shortest distance. In spacetime, the straight world line between two events is the longest proper time. Terra's straight path means she experiences more time. Stella's curved path means she experiences less. The twin who ages less is the one who took the non-straight path through spacetime. Acceleration happens to be what causes the path to bend, but the acceleration itself isn't the reason for the time difference. The reason is geometry, the shape of the path. Both explanations are correct. They're two ways of describing the same thing. The math works out the same either way. But the second explanation, the one about paths through spacetime, is deeper. It connects time dilation to the structure of spacetime itself. It shows that time is not something separate from space. It's part of a unified four-dimensional geometry, and how much time you experience depends on the shape of your path through that geometry. Move through space, and you move less through time. Stay still in space, and you move more through time. The faster you move through space, the slower you move through time. The speed of light is the limit where motion through time stops completely. A photon, traveling at light speed, experiences no time at all. From a photon's perspective, if it had one, its entire journey from emission to absorption happens in an instant. Zero elapsed time, infinite distance, zero duration. That's the foundation, the theory. Now let's talk about the evidence, because this isn't just a thought experiment. Time dilation is real, it's been measured, and it affects technology you use every day. The most direct test of the twin paradox involved atomic clocks and airplanes. In 1971, physicists Joseph Haefele and Richard Keating took 4 cesium beam atomic clocks, the most accurate timekeeping devices available at the time, and flew them around the world on commercial airliners. 2 clocks flew eastward, 2 flew westward. They compared the traveling clocks to reference clocks that stayed on the ground at the United States Naval Observatory. The prediction from special relativity was that the clocks on the planes would run slower than the ground clocks because they were moving. The prediction from general relativity, Einstein's theory of gravity, was that the clocks on the planes would run faster than the ground clocks because they were higher up, farther from Earth's gravitational field, and time runs faster in weaker gravity. Both effects are real. Both had to be calculated. The net result depended on the direction. Eastward flights move with the Earth's rotation, so the planes are moving faster relative to an inertial frame centered on Earth's axis. Westward flights move against the rotation, so they're moving slower. The eastward clocks should lose more time. The westward clocks should gain time. That's exactly what happened. After the flights, the clocks were compared. The eastward clocks had lost 59 nanoseconds compared to the ground clocks. The westward clocks had gained 273 nanoseconds. The predictions matched the measurements within experimental error. Time dilation is real. Clocks that move run slower. Not by much at aeroplane speeds, nanoseconds, but measurable, confirmed. The effect is even more important for GPS satellites. The global positioning system relies on extremely precise timing. Each satellite carries an atomic clock and broadcasts a signal that includes a timestamp. Your GPS receiver picks up signals from multiple satellites, compares the timestamps, and uses the differences to calculate your position. The system needs to know the time to within a few nanoseconds. Any error in the clocks translates to an error in your location. Nanoseconds of timing error turn into meters of position error. And GPS satellites are moving fast, about 14,000 kilometers per hour, and they're high up, about 20,000 kilometers above the surface, where gravity is weaker. Both effects matter. Special relativity says the clocks on the satellites should run slower because they're moving, about 7 microseconds per day slower. General relativity says the clocks should run faster because they're in weaker gravity, about 45 microseconds per day faster. The net effect is that the satellite clocks run about 38 microseconds per day faster than clocks on the ground. That's not a small correction. 38 microseconds per day adds up. If you didn't account for relativity, GPS would accumulate errors of about 10 kilometers per day. Your navigation system would be useless, but engineers do account for it. The satellite clocks are programmed to tick at a slightly slower rate before launch, so that once they're in orbit, once the relativistic effects kick in, they tick at the same rate as ground clocks. Relativity is built into the system. Every time you use GPS, every time your phone tells you where you are, you're relying on corrections for time dilation. You're using Einstein's equations. The twin paradox is not a curiosity, it's infrastructure. There's an even more dramatic confirmation. In 2015, NASA astronaut Scott Kelly spent nearly a year aboard the International Space Station, while his identical twin brother, Mark Kelly, stayed on Earth. The experiment wasn't primarily about relativity, it was a biomedical study, but the time dilation effect was real and measurable. The ISS orbits at about 27,500 kilometers per hour. At that speed, special relativity predicts that time should run slightly slower for Scott. But the station is also in a weaker gravitational field than the surface, so general relativity predicts time should run slightly faster. The special relativity effect is larger. The net result is that Scott's clock ran slower. By the end of the mission, Scott had aged about 8.6 milliseconds less than Mark. Not much, less than 1/100th of a second, but real, measurable, confirmed by comparing timestamps and biological markers. Scott was younger, not by a year, not by a day, but by milliseconds. The twin paradox, played out with actual twins, on a scale small enough that the effect is tiny, but large enough that we can detect it. Extend the scenario. Imagine Stella's trip wasn't to a nearby star, but to a distant galaxy. Imagine she traveled at 99.99% of the speed of light. The Lorentz factor at that speed is about 70. For every year Stella experiences, 70 years pass on Earth. She could travel for what feels like 10 years, turn around, come home, and find that 1,400 years have passed. Everyone she knew is dead. Civilizations have risen and fallen. The language has changed. The technology is unrecognizable. She's 20 years older. The Earth is 14 centuries older. She's not traveling through time in the sense of a time machine. She can't go backward. She can't visit the past, but she's traveling into the future, Earth's future. She's skipping over centuries of history by moving fast enough that time slows down for her. This is real. This is allowed by the laws of physics. This is how you get to the future without waiting for it to arrive. You move fast. And the universe lets you skip. The implications for interstellar travel are profound. The distances between stars are enormous. The nearest star system, Alpha Centauri, is about 4.3 light-years away. Even traveling at the speed of light, which we can't do, it would take 4.3 years to get there from Earth's perspective. But from the perspective of a traveler moving at light speed, the trip would be instantaneous. No time would pass at all. Travel at 99% of light speed, and the trip takes about 4.3 years from Earth, but only about 7 months for the traveler. Travel at 99.9%, and it's less than 2 months. The faster you go, the less time you experience. The distance contracts in your frame. What looks like 4.3 light-years to someone on Earth looks like a fraction of a light-year to you. You can cross interstellar distances in a human lifetime, in a fraction of a human lifetime, but when you arrive, everyone you left behind has aged. The people on Earth have experienced years or decades, while you experienced months. You can't come back to the same time you left. The future is waiting, and the faster you travel, the further into the future you go. This isn't science fiction, this is physics. The only barrier is engineering. Building a spaceship that can reach 99% of light speed is beyond anything we can currently do. The energy requirements are staggering. The fuel mass needed to accelerate a ship to those speeds is prohibitive. The hazards, collisions with interstellar dust, radiation exposure, navigational errors are severe. But nothing in the laws of physics forbids it. Time dilation is real. If we solve the engineering problems, if we build the ships, the universe will let us travel, and the travelers will age less. That's not optional. That's not something you can turn off. It's built into the structure of space-time. Move fast, and time slows down. That's the deal. That's the rule. And the rule has been tested and confirmed in every experiment designed to check it. There's one more layer to this. Time dilation affects everything. Not just clocks, not just heartbeats. Every physical process, radioactive decay, chemical reactions, biological aging, the firing of neurons, the replication of DNA. If you're moving at relativistic speeds, all of those processes run slower from the perspective of someone at rest. You think slower, you age slower, you live slower. But from your own perspective, nothing feels different. Your clock ticks at 1 second per second. Your heart beats at its normal rate. Time feels normal because time is normal for you. It's only when you compare your clock to someone else's clock, someone who stayed at rest or moved at a different speed, that you see the difference. Time is not universal, it's personal. It depends on your path through space-time, your history, your motion. Two people who start at the same event and meet at a later event can experience different amounts of time in between. That's not a flaw in the universe. It's a feature. Time is relative, and that means simultaneity is relative. Events that are simultaneous in one frame are not simultaneous in another. There is no universal now. No cosmic moment that slices through space-time and defines what is happening everywhere at once. Now is local. Now depends on where you are and how you're moving. Two events that happen at the same time, from your perspective, happen at different times from someone else's perspective. The universe doesn't have a single timeline. It has a web of timelines, intersecting, diverging, each one valid from its own frame of reference. And the twin paradox is the simplest, clearest demonstration that this is not just abstract philosophy, it's how reality works. The paradox is resolved. There's no contradiction. The traveling twin ages less because the traveling twin accelerated, or because the traveling twin took a non-straight path through space-time. Both descriptions are correct. Both lead to the same prediction. And the prediction is confirmed by atomic clocks on airplanes, GPS satellites, astronauts on the space station, particle accelerators where unstable particles live longer when they're moving fast, cosmic rays that reach the ground when they shouldn't because time dilation extends their half-lives. Every test we've ever designed to check this. Time dilation is real. The twin paradox is real. And if you ever get on a spaceship fast enough to make the effect noticeable, you will age less than the people you leave behind. That's the price of speed, or the reward, depending on whether you want to skip forward through time. But time dilation isn't the only way the universe behaves strangely when you zoom out far enough. We've been talking about twins, stars, spaceships, distances measured in light years. What happens when you zoom out further? When you stop thinking about trips across the galaxy and start thinking about the entire universe? What happens when you ask how big it is, whether it has an edge, whether there's anything beyond it? The observable universe has a boundary, a horizon. Not because space ends there, but because light from beyond that distance hasn't had time to reach us. But if space goes on forever, if the universe is infinite, then there are regions out there, infinitely far away, that we will never see. And in those regions, things could be happening. Anything could be happening. Stars, galaxies, planets identical to Earth, people identical to you. Infinite space means infinite possibilities. And infinite possibilities means that somewhere, out there, beyond the horizon, there's another version of this exact moment. Another version of you, reading these words, thinking these thoughts, wondering whether the universe really goes on forever. That's not science fiction. That's a consequence of infinity. And infinity has consequences we're only just beginning to understand. The twin paradox told us that time is not what we thought it was, that the clock ticking on your wrist and the clock ticking on a spaceship racing away from you are not measuring the same thing, that two people starting at the same moment can arrive at the same destination having aged different amounts, that motion through space costs you motion through time, that the faster you go, the more future you skip. The universe lets you travel forward through time by simply moving fast enough. No wormholes required, no exotic matter, just speed. And the price is that everyone you left behind ages without you. The Earth turns, seasons pass, decades pile up. And you, racing through the cosmos at 99% of light speed, you experience months while they experience years. Time is personal. Time is relative. Time depends on the path you take through space-time. But time isn't the only thing that's relative. Space is too. And when you zoom out far enough, when you stop thinking about spaceships and twins and trips to nearby stars, when you pull back and look at the entire universe, the whole thing, all of it, you run into a different kind of problem. A problem that doesn't involve acceleration or Lorentz factors or atomic clocks on airplanes. A problem that's simpler and stranger and more fundamental. The problem is this: we don't know how big the universe is. We can see only part of it, a finite bubble. And beyond that bubble, beyond the edge of what light has had time to reach us from, there could be more, a lot more, possibly an infinite amount more. And if the universe is infinite, if space goes on forever in every direction with no edge and no boundary and no end, then sitting out there, right now, beyond the horizon we can never cross, are things we can never see, galaxies we can never visit, events we can never know about, and copies, infinite copies of everything, of you. That's not speculation, that's a consequence of infinity. And infinity is where the next paradox lives. Start with what we can see, the observable universe. The word observable is doing a lot of work there. It doesn't mean the whole universe. It means the part of the universe we can observe, the part whose light has had time to reach us. The universe, as far as we know, is about 13.8 billion years old. It began with the Big Bang, a moment when all of space and time and energy erupted from a state of unimaginable density and temperature. Since then, the universe has been expanding. Space itself is stretching. Galaxies are moving apart. And light, traveling at 300,000 kilometers per second, has been racing outward from every point in every direction, carrying information about where it came from. But light only travels so fast, and the universe is only so old. which means there's a limit to how far we can see. Not because space ends, because time does, or rather, time has a beginning. 13.8 billion years ago, nothing existed. No space, no time, no light. Then the Big Bang. Then expansion. Then, after about 380,000 years, the universe cooled enough for hydrogen atoms to form. Before that moment, the universe was a hot, opaque fog of plasma. Photons couldn't travel freely. They scattered off charged particles constantly. The universe was glowing, but you couldn't see through it. Then the fog cleared. Electrons combined with protons. Neutral atoms formed. Photons decoupled. They started traveling in straight lines, and the light from that moment, the moment the universe became transparent, is still traveling. It's the oldest light in the universe, and we can see it. We call it the cosmic microwave background, the CMB. A faint glow of radiation coming from every direction in the sky, stretched by 13.8 billion years of expansion into microwaves. It's the edge of our observation, not a physical wall, not a boundary in space, a boundary in time. The CMB is as far back as we can see, because before it, there was nothing to see. The universe was opaque. So the observable universe has a radius, about 46.5 billion light-years. Wait, you might think, how is that possible? If the universe is 13.8 billion years old, shouldn't light have only traveled 13.8 billion light-years? Shouldn't the radius be 13.8 billion, not 46? The answer is expansion. Space itself has been stretching while the light was traveling. A photon that was emitted 13.8 billion years ago has indeed been traveling for 13.8 billion years, but the space it was traveling through was expanding the whole time. The galaxy that emitted the photon is now much farther away than it was when the photon left. The current distance to that galaxy, accounting for all the expansion that's happened since, is about 46.5 billion light-years. That's the radius of the observable universe, a sphere centered on us, containing everything whose light has had time to reach us. About 200 billion galaxies, trillions of stars, uncountable planets, all contained in a bubble roughly 93 billion light-years across. That's what we can see. Now ask the obvious question, what's beyond that? The honest answer is, we don't know. The light from beyond the observable horizon hasn't reached us yet. It might never reach us. Because the universe is not just expanding, it's accelerating. The rate of expansion is increasing. Distant galaxies are receding faster and faster. At some point, they're receding faster than light. Not because they're moving through space faster than light, which is forbidden, but because space itself is expanding so fast that the distance between us and them is growing faster than light can close the gap. Those galaxies are moving away from us at superluminal speeds. Their light will never reach us. Not in 13.8 billion years, not in 1 trillion years, not ever. They are beyond our causal horizon. We cannot interact with them. We cannot see them. We cannot send signals to them. They are, for all practical purposes, in a different universe. A region of space causally disconnected from ours, forever. But here's the thing, that region still exists. The universe doesn't care whether we can see it. Space keeps going. The laws of physics keep operating. Stars keep forming. Galaxies keep colliding. Planets keep orbiting. All of it happening out there, beyond the edge of the observable universe, completely inaccessible to us, and there's no reason to think it's different from what we can see. The cosmological principle, one of the foundational assumptions of modern cosmology, says the universe is homogeneous and isotropic. Homogeneous means it's the same everywhere. Isotropic means it looks the same in every direction, no special locations, no preferred orientations. The laws of physics are the same. The average density of matter is the same. The distribution of galaxies is the same. What we see in our local patch is representative of the whole. If that's true, and all observations so far suggest it is, then the universe beyond the observable horizon is just more of the same. More galaxies, more stars, more planets, more stuff, stretching outward, possibly forever. That brings us to the question of whether the universe is finite or infinite. And the answer is, we don't know, we can't know. Not from observations, because we can only see the observable universe. If the total universe is larger than the observable part, we can't see the extra. If it's infinite, we definitely can't see the infinite part. We're stuck inside a bubble and we can't see outside. The best we can do is measure the shape of the observable universe and extrapolate. The shape is called curvature. Space can be curved. General relativity tells us that. Mass and energy curve space-time, and on the largest scales, the overall density of the universe determines the curvature of space itself. 3 possibilities: positive curvature, like the surface of a sphere, negative curvature, like a saddle, or flat, like a sheet of paper. If the universe has positive curvature, it's finite but unbounded. You could travel in a straight line and eventually come back to where you started. A 3-dimensional version of walking around the surface of the Earth. If it has negative curvature, or if it's flat, it could be infinite. Space goes on forever. Or it could still be finite if it loops back on itself in some weird topology, but that's more speculative. Observations of the cosmic microwave background, the oldest light in the universe, tell us the curvature is flat, or at least very close to flat. So close that we can't detect any deviation. The observable universe is, within measurement error, spatially flat. That doesn't tell us whether the total universe is infinite. Flat space can be finite or infinite. But it does tell us that if the universe is finite, it's much larger than the observable part. How much larger? Estimates based on the flatness measurements suggest that if the universe is closed, if it curves back on itself, the total size must be at least 400 times larger than the observable universe, possibly much more. That's a minimum, a lower bound. The actual size could be vastly larger. Or it could be infinite. We can't tell from inside our bubble. Here's where infinity starts to bite. If the universe is infinite, and if the cosmological principle holds, meaning the laws of physics and the distribution of matter are the same everywhere, then infinity has consequences. Disturbing consequences. Because infinity doesn't just mean more stuff, it means all possible arrangements of stuff. Every possible configuration of atoms, every possible history, every possible outcome. And if space is infinite, then every configuration that's possible must occur somewhere, not just once, infinitely many times, including this one, including you. There are only so many ways to arrange a finite number of particles in a finite volume of space. The number is huge, unimaginably huge, but finite. Take a volume the size of the observable universe, fill it with particles, count how many different ways you can arrange those particles. The number is something like 10 to the power of 10 to the power of 120. That's 1 followed by 10 to the 120th zeros. That's not a number you can write down. It's not a number you can think about, but it's finite. And if space is infinite, then somewhere out there, far beyond the horizon, there's another volume of space the same size as our observable universe, containing particles arranged in exactly the same way. Same galaxies, same stars, same planets, same Earth, same you, reading the same words. thinking the same thoughts, wondering whether the universe is infinite. That's not philosophy, that's statistics. If the universe is infinite, and if matter is distributed more or less evenly, then every possible arrangement happens, and every arrangement that happens once happens infinitely many times. You're not unique, you're one instance in an infinite set. Somewhere out there, infinitely far away, is another version of you, identical down to the atom. Same memories, same experiences, same decisions. And another version where you made one different choice. And another where you made two different choices. Every possible variation. All of them exist. All of them are real. All of them are you, or copies of you, or versions of you. The terminology breaks down because identity breaks down when you have infinite duplicates. That's the paradox of an infinite universe, not a logical contradiction, an ontological nightmare. The idea that if space goes on forever, then you are not singular, you are plural, infinitely plural, and there's no way to ever meet your duplicates. They're beyond the horizon, beyond the reach of light, beyond causality. You can never interact with them. You can never confirm they exist. But if the universe is infinite, they must exist. The math demands it. Some physicists hate this conclusion. They argue that the cosmological principle doesn't hold at arbitrarily large scales, that maybe the universe is infinite, but maybe matter isn't distributed evenly everywhere. Maybe there are regions where the density drops off, where galaxies become sparse, where eventually, far enough out, there's just empty space, no duplicates, no copies, just void. That's possible, but there's no evidence for it. Every observation we have suggests the universe is homogeneous on the largest scales we can measure. Extending that to infinity is an extrapolation, yes, but it's the simplest extrapolation. The alternative requires adding structure, adding variation, adding reasons why the universe would be different out there than it is here. Occam's razor says, don't multiply entities beyond necessity. The simplest assumption is that it's the same everywhere. And if it's the same everywhere, and space is infinite, then duplicates are inevitable. Others argue that the universe is finite, that it must be finite because infinity is too strange, too uncomfortable, too incompatible with the idea that we're unique, that our lives matter, that the choices we make are meaningful. If there are infinite copies of you making every possible choice, then what does it mean for you to choose? Are you choosing, or are you just playing out one thread in an infinite tapestry where all threads exist? That's a philosophical question, not a physical one. Physics doesn't care whether infinity makes you uncomfortable. Physics cares whether the equations predict it, and the equations allow it. General relativity allows infinite space. Quantum field theory works fine in infinite space. There's no law of physics that forbids the universe from being infinite. The only question is whether it is. We may never know, because the observable universe is all we get. The expansion of space, driven by dark energy, is accelerating. Distant galaxies are moving away faster and faster. The size of the observable universe is actually shrinking in a certain sense. Not in physical size, that's still growing, but in content. Galaxies that are currently visible will eventually cross the horizon. Their light will redshift into invisibility. They will disappear. Billions of years from now, if intelligent civilizations still exist, they will look at the sky and see far fewer galaxies than we see today. The universe will look emptier, darker. The cosmic microwave background will cool further, fade further, become harder to detect. Eventually, in the far future, the CMB might be undetectable, and any astronomers alive then, looking at the sky, would see a nearly empty universe. A few nearby galaxies, nothing else. They would have no evidence of the Big Bang, no evidence of cosmic expansion, no evidence of the larger universe beyond their local group. They would be trapped in a bubble even smaller than ours, with no way to know that anything else existed. The universe would forget its own history. The evidence would evaporate, quite literally, as photons redshift into nothingness. That's called the cosmic horizon problem. It's not a problem in the sense of a flaw. It's a problem in the sense of a limitation, a fundamental epistemic barrier. There are things we cannot know because the information has not reached us. There are things we will never know because the information will never reach us. And there are things future observers will not be able to know because by the time they exist, the information will have faded beyond detection. The universe is not obligated to reveal itself. It's not obligated to leave clues. The accident of when and where you exist determines how much you can see. We live in a privileged time. The universe is old enough that structures have formed, galaxies, stars, planets, but it's young enough that we can still see the CMB. We can still measure the expansion. We can still detect distant galaxies. We can still piece together the history of the cosmos. A few 100 billion years from now, that won't be possible. The universe will still be here, but the evidence of its origin will be gone. The cosmological principle will still hold, but verifying it will be impossible. Future astronomers will have to take it on faith, or invent it from scratch, or never discover it at all. Observations of the curvature, combined with measurements of the CMB, give us a lower bound on the size of the universe. If the universe is finite, if it's shaped like a higher dimensional sphere, then the minimum radius is about 18 trillion light-years. That's the smallest it could be and still produce the flatness we observe. The actual radius could be much larger, or infinite. We don't know. But we do know that if it's finite, it's at least that big. And that means there are regions of space we will never see. Not because they're too far, because the light hasn't had time to get here yet. And with accelerating expansion, it never will. Those regions are real. They contain galaxies, stars, planets, possibly life, possibly intelligence, possibly civilizations asking the same questions we're asking. And we will never know. They will never know about us. We are causally disconnected, forever. The observable universe contains about 200 billion galaxies. If the total universe is at least 400 times larger, which is the conservative estimate, then the total number of galaxies is at least 80 trillion, possibly far more, possibly infinite. Each galaxy contains hundreds of billions of stars. Each star could have planets. The number of worlds in the total universe, even if it's finite, is so large that it might as well be infinite. And we can see only a tiny fraction. We are looking at a sliver of reality, a patch, a sample. The rest is out there, existing without us, unobservable and unknowable. That raises a question about meaning. If the universe is infinite, or even if it's just vastly larger than the part we can see, does that diminish us? Does it make our existence less significant? Are we just one random fluctuation in an infinite sea of fluctuations, one instance in an infinite set? The universe doesn't answer that. The universe doesn't care about significance. It doesn't assign meaning. It just exists. Whether you find meaning in being unique or in being part of an infinite pattern is not a question physics can answer. That's on you. But there's another angle. If the universe is infinite, then somewhere out there, beyond the horizon, is a copy of Earth, a perfect duplicate, same history, same people, same events, and also a near duplicate where one thing is different, and another where two things are different, and so on, every possible variation. All of them real, all of them happening right now, and you can never reach them, you can never verify they exist. But if infinity is real, they must exist. The odds of them not existing are zero. Not small, zero. Infinity doesn't allow exceptions. That also means somewhere out there is a version of Earth where you made different choices, where you took the other job, where you moved to a different city, where you said yes instead of no. And that version of you is living a different life. And another version made yet another choice. And on and on. Every decision tree branches. Every branch exists somewhere in the infinite expanse. You're not living one life. You're living one instance of infinitely many lives. The others are out there, unreachable, unknowable, but real. This isn't the many worlds interpretation of quantum mechanics. That's a different thing. That's about quantum superpositions splitting into parallel branches at every measurement. This is simpler. This is just space being big enough that every configuration happens. No quantum mechanics required, just infinity. And infinity is brutal. It doesn't care about uniqueness. It doesn't care about rarity. If something is possible, it happens. If it happens infinitely many times. That's the rule. That's what infinity means. So where does that leave us? Stuck inside a bubble. The observable universe, 46.5 billion light-years in radius, expanding, accelerating, pushing more and more galaxies beyond our reach. We can see a finite patch, we can measure it, we can map it, we can study it, but beyond that patch is more, possibly infinite more, and we will never know for certain. We can extrapolate. We can assume the cosmological principle holds. We can calculate lower bounds on the total size, but we cannot observe it. The information is not available. The light has not arrived. The causal connection does not exist. We are fundamentally limited, not by technology, not by budget, not by time, by the speed of light and the age of the universe, by the structure of space-time itself. That's the paradox. The universe might be infinite, or it might just be unimaginably large. Either way, most of it is hidden from us, permanently. And if it's infinite, then everything that can happen does happen, somewhere. Including versions of this exact moment playing out in infinite variations across infinite space. You are here, you are also there, infinitely many theirs, doing infinitely many things. And the version of you reading this right now, in this moment, in this particular arrangement of atoms on this particular planet, is just one thread in an infinite tapestry. The universe doesn't end where our observations end. It keeps going. Stars keep forming. Galaxies keep colliding. Planets keep orbiting stars that we will never see. Life might arise. Civilizations might flourish. Questions might be asked. Answers might be sought. All of it happening beyond the horizon. All of it real. All of it inaccessible. We are not seeing the whole picture. We are seeing a frame, a snapshot, a fragment. The rest is out there, but it's not for us. The universe has drawn a line, this far, no further. Not because it's cruel, because that's how space-time works. Information travels at light speed. The universe is finite in age. Combine those facts and you get a horizon, a boundary not in space but in time. A limit not on where you can go, but on what you can know. And that leads to a different kind of question, a question that's not about space or time or horizons or infinity, a question about you, about agency, about choice. Because if the universe is infinite and every possible version of you exists somewhere, then what does it mean for you to choose? Are your choices yours? Or are they just one path through a possibility space where all paths are realized? If every outcome happens, does your outcome matter? If the laws of physics are deterministic, if every particle's motion is governed by equations, If the future is determined by the past, then where does free will fit? Are you choosing, or are you just watching a movie that was written at the Big Bang? That's not a paradox about space. That's a paradox about you, and it's where we're going next. The paradox of an infinite universe left us staring at a horizon we can never cross, a boundary not in space but in time, a limit not on where we can go but on what we can know. The observable universe is all we get, 46.5 billion light-years in radius, 200 billion galaxies, trillions of stars, uncountable planets, and beyond that, possibly forever, more of the same. More galaxies we'll never see, more stars that will never send us their light. And if space is truly infinite, then somewhere out there, beyond the reach of observation, beyond the causal horizon, are copies, infinite copies, of everything, of you, living every possible variation of the life you're living, making every possible choice you didn't make, every decision tree branching into reality somewhere in the infinite expanse. You are singular here, plural there. One thread in an infinite tapestry where all threads exist. That picture is unsettling enough on its own, but it raises a question that cuts deeper than cosmology. A question that doesn't require telescopes or redshift measurements or calculations about the curvature of space. A question you can ask right now, sitting where you are, without looking up at the sky or wondering what's beyond the horizon. The question is this: if the universe is governed by laws, if every particle follows rules, if every event is the inevitable consequence of the events that came before it, then where do you fit? Where does choice fit? When you decided to read this, when you chose to pay attention or let your mind wander, when you made any decision today or yesterday or ever, was that actually you, or was it just physics, atoms obeying equations, neurons firing in patterns determined by chemistry and electricity and the state of your brain 1 millisecond earlier? A cascade of cause and effect stretching back to the Big Bang, playing out on autopilot, with you as a passenger who thinks he's driving. That's the paradox of free will, and it's the oldest, deepest, most personal paradox on this list. Because unlike the others, unlike Olbers or Fermi or the grandfather or the Bootstrap or Schrödinger or Zeno or black holes or twins or infinite space, this one isn't about the universe out there. It's about you in here. It's about whether the thing you call choice, the experience of deliberating and deciding and acting, is real or an illusion. Whether you have agency or whether you're a deterministic machine that's convinced itself it's free. And depending on how you answer that question, everything changes. Morality changes, responsibility changes, meaning changes. The entire structure of how you think about yourself and your place in the world hinges on whether the sense of control you feel when you make a decision corresponds to anything real, or whether it's just a story your brain tells itself after the fact. Let's start with the terms, because this paradox has been argued about for thousands of years and the vocabulary matters. Determinism, in the scientific context, is the idea that every event is causally determined by prior events, that the state of the universe at one moment, combined with the laws of physics, uniquely determines the state of the universe at the next moment. There's only one possible future. Everything that happens was always going to happen, not because someone planned it, not because fate or destiny or gods are pulling strings, because the laws of physics are what they are, and given the initial conditions, given the exact position and momentum and energy of every particle at the beginning, the entire history of the cosmos unfolds mechanically. Like a computer running a program, the output is determined by the input. There's no wiggle room, no alternative timelines. No other way it could have gone. Free will, in the traditional philosophical sense, is the capacity to make choices that are not determined by prior events, the ability to do otherwise. If you chose coffee this morning, free will means you could have chosen tea, really could have. Not just in the sense that no one was holding a gun to your head. In the sense that even if you rewound time, even if you put the universe back to the exact state it was in 1 second before you chose, you might choose differently. The choice is genuinely open. It's not fixed by the past. It's not locked in by the laws of physics. You, the agent, the conscious decision maker, have the power to tip the scales, to break the chain of causality and introduce something new. A decision that wasn't determined, a choice that was yours. Those two ideas, determinism and free will, don't play well together. If determinism is true, if the state of your brain at any moment is fully determined by the state of your brain 1 moment earlier, and that state was determined by the state before it, and so on, all the way back to your birth, to your parents' genes, to the environment you grew up in, to the motion of atoms in the early universe, then your choices aren't really choices, they're outputs, predetermined outputs. You are always going to choose coffee. You couldn't have chosen tea, not because you were forced, because the physics didn't allow for it. Your neurons were going to fire in that pattern. The chemistry was going to cascade in that direction. The feeling of choosing, the sense that you were deliberating and weighing options and then deciding, all of that was window dressing. The decision was made before you became aware of it. You just didn't know it yet. That's the hard determinist position. The idea that free will is an illusion, that we are biological machines, extraordinarily complex machines, but machines nonetheless, and machines don't choose, they compute. They process inputs and generate outputs according to their programming. Your programming is your brain. Your inputs are your sensory experiences, your memories, your emotions, your neurochemistry. Your outputs are your decisions, and the whole process is governed by the laws of physics, electromagnetism, quantum mechanics, biochemistry. No magic, no ghosts. No immaterial soul reaching down from some non-physical realm to nudge your neurons in a direction they weren't already going. Just matter obeying rules. And if that's all you are, then free will is not just absent, it's incoherent. It's a category mistake. Like asking what color the number 7 is, or what the sound of blue tastes like. The question doesn't make sense because the thing being asked about doesn't exist. Neuroscience has made this picture harder to ignore. In the 1980s, a researcher named Benjamin Libet ran experiments that became infamous in the free will debate. He asked subjects to perform a simple task. Flex your wrist whenever you feel like it. Spontaneous decision. No external cue. Just wait until you feel the urge, then move. While they did this, Libet measured their brain activity using electrodes on the scalp. And he asked them to note the exact moment they became aware of the decision to move. The moment they felt the intention. The subjective experience of choosing. What he found was that the brain activity associated with initiating the movement, a signal called the readiness potential, started ramping up about half a second before the subjects reported being aware of the decision. The brain was preparing to move before the person consciously decided to move. The decision, or at least the neural precursor to the decision, happened first. The conscious awareness of the decision came later, hundreds of milliseconds later. That result has been replicated and refined in multiple studies over the decades. In some experiments, researchers using functional MRI scanners could predict which hand a subject was about to move up to 10 seconds before the subject became consciously aware of the choice. 10 seconds. That's not a delay in reporting. That's not reaction time. That's the brain deciding, unconsciously, and then the conscious mind catching up later and claiming credit. The story you tell yourself, "I decided to move my left hand," is a post hoc narrative. The decision was already made by unconscious processes. You became aware of it after the fact and experienced that awareness as the moment of decision. But you were wrong. The decision happened earlier, below the threshold of consciousness. In neural circuits you don't have access to and can't control. You didn't choose. Your brain chose. Then it informed you. And you, the conscious observer, interpreted that information as your own intention. That's deeply unsettling, because it suggests that the experience of making a decision, the feeling of deliberating and then choosing, is not the cause of the action. It's a byproduct, a side effect. The action was already initiated by the time you became aware of wanting to do it. Consciousness is not in the driver's seat. It's in the passenger seat, watching the road go by, convinced it's steering. But the wheel is being turned by processes you're not conscious of. By neural activity shaped by genetics, by past experiences, by neurochemistry, by sensory inputs, all of it churning away beneath the surface, generating outputs that bubble up into awareness and feel like decisions. But they're not decisions in the sense you thought. They're the result of a deterministic or at least mechanistic process that was running before you showed up. If that's true, then what happens to responsibility? If you didn't choose your actions, if your actions were the inevitable result of your brain state, and your brain state was the inevitable result of prior causes going back to your childhood, your genes, the environment, all the way back to the initial conditions of the universe, then how can you be held responsible for what you do? Responsibility seems to require that you could have done otherwise, that you had a choice and you made the wrong one. But if determinism is true, you couldn't have done otherwise. You were always going to do what you did. So how can you be blamed? How can you be punished? How can anyone be blamed or punished for anything if all actions are the output of deterministic processes over which no one has ultimate control? Some philosophers bite the bullet. They accept that traditional notions of moral responsibility don't hold up under determinism, that punishment as retribution is unjustified, that people do what they do because of causes beyond their control, and while society might need to intervene to prevent harm, warehousing people in prisons and calling it justice is incoherent if no one is truly responsible for their actions. Others take a different route. They argue for compatibilism, the idea that free will and determinism can coexist, that you don't need the ability to do otherwise to be free. What you need is for your actions to flow from your own desires, your own preferences, your own internal states. If you chose coffee because you wanted coffee and no one forced you and no external constraint prevented you, then that's enough for free will. It doesn't matter that your desire for coffee was caused by your neurochemistry and your past experiences. It's still your desire. You acted on it. That's freedom, not freedom from causality, freedom to act according to your own nature. Compatibilism redefines free will. It says free will is not about breaking the chain of causality. It's about the chain running through you in the right way. If your actions are caused by your beliefs and desires, then you're free. If your actions are caused by someone else forcing you, or by a brain tumor, or by direct manipulation of your neurons by an external agent, then you're not free. The distinction isn't between determined and undetermined. It's between determined by you and determined by something else. And as long as the determination flows through your decision-making processes, through your deliberation, through your evaluation of reasons, then it counts as free will. You're still a machine. But you're a machine that reflects, that weighs options, that integrates information and generates preferences. And that's enough. Critics of compatibilism call it a dodge. They say it's redefining the terms to avoid the problem, that it's not real free will if the outcome was determined all along, that calling it freedom when you couldn't have done otherwise is linguistic sleight of hand. The hard incompatibilists, the people who think free will and determinism cannot coexist, argue that if your actions are determined, you're not free, no matter how much it feels like you are. And if your actions are random, which we'll get to in a moment, you're also not free, because random isn't choice. Random is just noise. So whether the universe is deterministic or indeterministic, free will in the traditional sense is impossible. Either your actions are caused by prior states, in which case they're determined and you couldn't have done otherwise, or they're not caused by anything, in which case they're random and you still didn't control them. Either way, there's no room for the kind of free will that most people intuitively believe in, the kind where you're the ultimate source of your decisions, where the buck stops with you, where you could have chosen differently if you'd wanted to. This is where quantum mechanics enters the picture, because for a long time the universe was thought to be entirely deterministic. Classical mechanics, Newton's laws, Maxwell's equations, all of them deterministic. Plug in the initial conditions, run the equations, get a unique answer. The future was fixed. But quantum mechanics changed that. At the smallest scales, at the level of particles and fields and wave functions, the universe is not deterministic. It's probabilistic. When you measure a quantum system, you get one of several possible outcomes, and the theory only tells you the probabilities. It doesn't tell you which outcome you'll get. The wave function gives you a distribution of possibilities. The measurement collapses the wave function to one outcome, but which one is not determined by the prior state. It's random, or at least it appears random. The orthodox interpretation says it is genuinely random. There's no hidden variable determining the outcome. The universe literally doesn't know which outcome will occur until it occurs. That randomness, some people argue, is the crack in determinism, the elbow room for free will. If the universe is not deterministic, if quantum events introduce genuine indeterminacy, then the future is not fixed. There are multiple possible futures, and maybe, just maybe, that indeterminacy bubbles up from the quantum level to the level of neurons and brain states and decisions. Maybe quantum effects in microtubules or ion channels or synaptic transmission introduce enough randomness that your brain state is not uniquely determined by its prior state. Maybe there's enough uncertainty, enough quantum fuzziness that your decision could go either way. And if that's true, then you're not a deterministic machine, you're a probabilistic one. And probability means possibility, multiple possible outcomes, not just one locked-in path. The problem with that argument is that randomness is not choice. If your decision is determined by a quantum coin flip, you didn't choose. The universe chose for you. Or more precisely, the universe rolled the dice and you got the result. That's not agency, that's chance. It's not determinism, fine, but it's not freedom either. You wanted the ability to control your decisions, to be the author of your actions. Replacing determinism with randomness doesn't give you that. It just replaces one form of lack of control with another. Instead of your actions being determined by the past, they're determined by random quantum events. You're still not in charge. You're still not steering. The steering is just being done by a random number generator instead of a deterministic calculator. Either way, you're along for the ride. Some philosophers argue that this misses the point. That quantum indeterminacy doesn't directly generate decisions, but creates space for top-down causation. The idea is that the brain is a complex system operating near the boundary between deterministic and chaotic behavior. Quantum uncertainty at the micro level could amplify through nonlinear dynamics to create macroscopic unpredictability. And within that unpredictability, within that space where the future is genuinely open, consciousness might play a role, not by violating physics, by exploiting the flexibility that physics allows, by guiding the system toward one attractor rather than another. The brain doesn't override the laws of physics, it navigates within them. And if the laws of physics are probabilistic, if they allow multiple paths, then maybe the conscious mind, whatever it is, helps select which path gets taken. Not randomly, not deterministically, but through a process that integrates information, evaluates outcomes, and tips the probabilities in a direction that reflects intention. That's a more sophisticated version of the free will argument. It doesn't require magic. It doesn't require breaking the laws of physics. It just requires that the laws of physics, at the quantum level, leave room for influence. And that consciousness, which we don't fully understand, which might be a fundamental feature of complex information processing systems, plays a role in that influence. The problem is that this is speculative. We don't have evidence that quantum effects are significant in neural processing. Most neuroscientists think the brain operates at a scale where quantum effects average out, where the randomness cancels and the behavior is effectively classical, deterministic, or at least statistically deterministic. And we definitely don't have evidence that consciousness can influence quantum outcomes. The idea that observation collapses the wave function is part of quantum mechanics, yes, but observation in the technical sense just means interaction with a macroscopic measuring device. It doesn't require a conscious observer. Photons don't need anyone watching them to collapse their wave functions. They just need to interact with something, anything, a detector, a molecule, another photon. Consciousness is not necessary for collapse. So the idea that conscious intention could somehow steer quantum outcomes is not supported by anything in the current physics. There's also the issue that even if quantum randomness does play a role in brain function, even if your neurons are influenced by quantum fluctuations, that doesn't automatically give you free will, it gives you randomness. And as we've already said, randomness is not control. If the difference between choosing coffee and choosing tea comes down to whether a particular ion channel opens because a quantum event nudged it one way or the other, then you didn't choose, a quantum fluctuation chose. You might experience it as a choice. You might feel like you deliberated and then decided. But the actual mechanism, the thing that tipped the balance, was random, not you, unless you want to argue that you are the quantum randomness, that your consciousness is somehow identical with, or emerges from, or supervenes on quantum processes in a way that makes the randomness intentional rather than arbitrary. But that's not a scientific claim, that's metaphysics, and it's not testable, it's not falsifiable. It's just a story you can tell yourself to avoid the conclusion that you don't have free will. So where does that leave us? The universe might be deterministic, in which case your actions are fully determined by prior causes and you couldn't have done otherwise. Or the universe might be indeterministic at the quantum level, in which case your actions are influenced by randomness and you still couldn't have done otherwise in any meaningful sense because the variation isn't coming from you, it's coming from chance. Either way, the traditional idea of free will, the idea that you are the ultimate uncaused cause of your decisions, the prime mover, the agent who could have chosen differently if you'd wanted to, that idea doesn't seem to fit. It doesn't fit with determinism. It doesn't fit with randomness. It doesn't fit with anything physics tells us about how the universe works. And yet you experience choice. You experience deliberation. You experience the sense that you are weighing options, considering reasons, and then deciding. That experience is real. It's not an illusion in the sense of being fake. It's a real feature of your mental life. When you think about whether to have coffee or tea, you genuinely feel like you're evaluating. You're running a simulation in your head. You're imagining outcomes. You're consulting your preferences, and then you make a call. The call might be determined by unconscious processes that happened before you were aware of deliberating. Fine, but the deliberation still happened. The evaluation still occurred. You didn't just act on reflex. You thought about it. And that thinking, that processing, that integration of information and preferences and predictions, that's not nothing. That's a real causal process. It's part of the chain. Your conscious deliberation is part of what determines your action. Not the only part, not the ultimate part, but a part, and maybe that's enough. Maybe free will doesn't require being outside the causal chain. Maybe it just requires being inside it in the right way. Being the kind of system that deliberates, that responds to reasons, that can reflect on its own desires and change them. That's something humans can do that thermostats can't. That's a difference that might matter. Compatibilists have been making versions of this argument for centuries. The ancient Stoics believed in determinism, but also believed in human responsibility, because responsibility, they said, was about acting in accordance with reason and virtue, not about having some mystical ability to violate causality. Modern compatibilists like Daniel Dennett argue that free will is real in the only sense that matters. It's the ability to make decisions based on your own goals and beliefs, to respond to incentives, to change your behavior when given new information, to be a rational agent navigating the world. That's freedom, not metaphysical freedom, not freedom from the laws of physics, but practical freedom. The freedom that allows you to function as a person, to be held accountable, to participate in moral and social life. And that kind of freedom is entirely compatible with determinism. It's also compatible with quantum randomness, because what matters isn't whether your actions were determined or random. What matters is whether they were yours, whether they came from your reasoning, your values, your deliberation. And if they did, then you're free in the way that counts. The hard incompatibilists aren't convinced. They say compatibilism is a compromise, a way to salvage the language of free will without the substance. That calling it freedom when you couldn't have done otherwise is just playing word games. That real free will, the kind people intuitively believe in, requires that you could have chosen differently. And if you couldn't, then you weren't free, period. The experience of freedom is an illusion, a useful illusion maybe, an evolutionarily adaptive illusion that helps you navigate a complex social world, but an illusion nonetheless. The conscious sense of choosing comes after the brain has already decided. You're not making decisions, you're observing them. You're the narrator of a story that's being written by someone else, by no one else, by the deterministic or probabilistic machinery of your neurons, which are doing what they were always going to do given the state they were in and the inputs they received. If that's true, if free will is an illusion, then what happens to meaning? If you didn't choose your life, if your decisions were all determined or random, then what were you doing? What was the point? The answer, if you're a hard determinist, is that meaning is also something you construct. It's not handed to you by the universe. The universe doesn't care about meaning. It doesn't assign purposes. Meaning is what you make of your experience. It's how you interpret what happens to you. And the fact that you didn't ultimately control what happened, the fact that your choices were part of a causal chain stretching back to the Big Bang, doesn't change the fact that you experienced them as yours, that you lived through them, that they mattered to you. Meaning is subjective. It's internal. It's the story you tell yourself. And that story is real, even if the freedom you thought was behind it isn't. But not everyone can live with that. Not everyone is comfortable accepting that their sense of control is a fiction, that their agency is a narrative overlay on a deterministic or random substrate. For a lot of people, the intuition that they have free will is so strong, so central to their self-concept, that giving it up feels like giving up something essential, like admitting that they're not really a person, just a puppet, or a robot, or a biological mechanism that happens to be self-aware but doesn't actually steer anything. That's existentially threatening, and the threat is part of why this paradox has been debated for so long, because the stakes aren't just philosophical, they're personal. They're about identity, about what it means to be you, about whether you matter, about whether anything you do is genuinely yours, or whether you're just a conduit for forces beyond your control. Physics doesn't resolve this. Physics tells you how particles behave, how fields interact, how energy flows through systems. It doesn't tell you whether you have free will. That's not a question physics can answer, because free will, at least in the traditional sense, isn't a physical property. It's a philosophical one. It's about agency, about hood, control, concepts that don't map cleanly onto the equations. You can describe a brain in physical terms. You can trace the flow of ions across membranes. You can map the firing patterns of neurons. You can predict behavior based on brain states. But whether any of that constitutes free will depends on how you define free will. And that's not a scientific question. That's a conceptual one, a definitional one, a question about what you're willing to count as freedom and what you're not. Quantum mechanics doesn't resolve it either. Quantum mechanics introduces randomness. It breaks determinism at the smallest scales. But randomness is not agency. It's not intention. It's not control. If your decisions are influenced by quantum fluctuations, that doesn't make them free. It makes them partly random. And randomness doesn't help. You wanted to be the author of your choices. You wanted to be in control. Quantum randomness doesn't give you that. It just adds noise to the system. The noise might make your behavior unpredictable. It might mean the future isn't fixed, but it doesn't mean you're steering. It means nobody's steering. The universe is rolling dice, and you're experiencing the results and calling them choices. That's not freedom. That's just indeterminism. And indeterminism is not the same thing as free will. So what's left? What's left is the experience. The subjective, first-person, undeniable experience of making choices, of deliberating, of weighing options, of deciding. That experience is real. It's part of your mental life. It's part of what it means to be conscious. And whether or not it corresponds to metaphysical free will, whether or not you could have done otherwise in some ultimate sense, the experience itself matters, because it's what shapes your behavior. It's what allows you to plan, to anticipate, to reflect, to learn. You might be a deterministic system, you might be a probabilistic system, but you're a system that models the future, evaluates possibilities, and adjusts its actions accordingly. That's not trivial. That's the kind of complexity that allows you to navigate the world in ways that simpler systems can't. And maybe that's what free will is. Not the ability to violate causality, not the power to do otherwise in an absolute sense, but the capacity to be the kind of system that deliberates, that responds to reasons, that can represent multiple possible futures and choose between them based on its own goals and values. That's something, that's real, and it's more than a rock has, more than a bacterium has, more than most things in the universe have. You're a structure in space-time that has the property of intentionality, of goal-directed behavior, of caring about outcomes. And that structure, that process, is what we call agency. It's not outside the laws of physics. It's an implementation of the laws of physics at a level of complexity where new properties emerge. Consciousness, self-awareness, choice. The paradox doesn't go away. Determinism and free will still pull in opposite directions, but maybe the resolution isn't choosing one over the other. Maybe it's recognizing that both are true in different senses. You're determined in the sense that your actions have causes. Your brain state at one moment determines your brain state at the next. Your decisions are the output of neural processes that follow physical laws. But you're also free in the sense that those processes are yours. They run through you. They incorporate your goals, your values, your history. They respond to reasons. They allow you to learn from mistakes, to imagine alternatives, to change course when new information arrives. That's not freedom from causality. It's freedom within causality. Freedom as the ability to be the kind of causal process that reflects, deliberates, and directs itself toward chosen goals. And that might be the only kind of freedom that's coherent, the only kind that's real, the only kind the universe allows. You are not separate from the universe. You are part of it. A small, temporary, extraordinarily complex part. A configuration of matter that has organized itself in such a way that it can look back at the rest of the matter and ask questions. What am I? Why am I here? Do I have control? And the universe doesn't answer. It just keeps running. But you, the small complex part, keep asking, keep deliberating, keep choosing. And whether those choices are determined or random or some combination of both, they're still happening. You're still experiencing them. You're still acting. You're still living. And in the end, maybe that's what matters. Not whether you could have done otherwise in some metaphysical sense, but whether you're doing something now. Whether you're engaging with the world. Whether you're the kind of system that cares about what happens next. Because caring, deliberating, choosing, even if those processes are deterministic, even if they're part of a causal chain you didn't start and can't escape, they're still yours. They're still real, and they're still the only thing that separates you from a universe that doesn't care at all. That's it for today, guys. I'll see you in the next one. Take care.